Look up tonight at the dark patch of sky behind Pluto. That emptiness you assume is empty, that cold, silent vacancy 4 billion miles from the sun, is not empty at all. It is crowded with ancient, frozen worlds older than Earth itself, drifting in slow procession through a darkness so deep it has its own architecture. A spacecraft is moving through them right now, and what it is finding rewrites what we thought lay beyond the last planet. Tonight, we will move outward through the solar system's most ancient and least understood region. From Pluto's strange mountains of ice, through the frozen archives of the Kuiper belt, past the cliff where our maps once ended, and into the wider darkness beyond, and understand why the edge of the solar system is not where anyone thought it was. Before we dive in, if you love exploring the outer solar system as much as we do, take a second to like the video or subscribe, and tell me where you're listening from and what time it is. Now, let's begin. There is a version of the solar system that most of us carry in our heads, a picture assembled from textbooks and classroom posters, and the kind of diagrams that hang on the walls of science museums. In that picture, the solar system is tidy. There is the sun at the center, hot and commanding. There are the inner rocky planets, Mercury, Venus, Earth, Mars, small and warm and close. Then the asteroid belt, a ring of rubble serving as a kind of border crossing. Then the gas giants, Jupiter, Saturn, Uranus, Neptune, enormous and cold and ringed and magnificent. And then, at the outermost edge of this orderly diagram, there is Pluto, small, lonely, a little demoted, a little pitied. And beyond Pluto, in that poster and that diagram and that picture in your head, there is simply nothing, a white margin. The page ends. That picture is not wrong in the way that a lie is wrong. It is wrong in the way that a map drawn before the explorers came home is wrong. Incomplete in ways that the map maker could not have anticipated, because the territory turned out to be far stranger, far more crowded and far more consequential than anyone suspected. The truth is that beyond Pluto lies one of the most remarkable structures in the known solar system. It is a region of space populated by hundreds of thousands of icy worlds, some of them the size of cities, some the size of countries, a few of them the size of small continents. It is a region where the building blocks of planets were flash frozen in place 4.5 billion years ago, preserved in the cold like insects in amber, holding within their geology and chemistry a record of what the solar system looked like in the very first moments of its existence. It is a region that our instruments barely reached until very recently, and which a single small spacecraft is still, right now, moving through, transmitting data back to Earth at the pace of a slow drip, revealing a world that is simultaneously ancient beyond comprehension and newly discovered. This is the Kuiper belt. And what NASA has found there, what a spacecraft called New Horizons has been finding, what telescopes like Subaru and Hubble and the James Webb Space Telescope have been finding, is not what anyone predicted. Pause here, because what follows will not fit into the tidy diagram. What follows requires that you hold a much larger picture in your mind. Not the picture from the poster, but the actual picture, the one assembled from decades of observations from a spacecraft traveling at 36,000 miles per hour, from spectrometers and dust counters and cameras pointed at objects so faint that detecting them requires stacking thousands of images on top of one another and listening for a signal that is almost lost in noise. The picture is this. The solar system does not end at Pluto. It does not end at the traditional outer boundary of the Kuiper belt. It may not end where we currently think it ends. And hidden in that larger truth is a set of implications that reach backward through planetary science, forward through our understanding of solar systems around other stars, and directly into the question of how worlds, including ours, come to exist at all. To understand what NASA found beyond Pluto, you first need to understand what we thought was there and why we thought it. That means going back, not to the beginning of the solar system, but to the beginning of our awareness of the solar system's outer edge. It means tracing a set of ideas that took shape slowly over decades as astronomers peered into the darkness and tried to make sense of the faint signals coming back. In 1930, a young astronomer named Clyde Tombaugh, working at the Lowell Observatory in Flagstaff, Arizona, discovered Pluto. He was 24 years old and had been hired specifically to search for a hypothetical ninth planet whose existence had been predicted, somewhat tenuously, on the basis of apparent gravitational irregularities in the orbits of Uranus and Neptune. The first astronomers to suggest the existence of a belt of objects beyond Neptune were actually Frederick C. Leonard in 1930 and Kenneth E. Edgeworth in 1943, though their ideas would take decades to gain traction. Tombaugh found Pluto, and the astronomical community celebrated, and the solar system felt complete. But it did not stay complete for long. Even as Pluto was being celebrated, a few theorists were quietly noting a problem. Pluto was too small, far too small, to have produced the gravitational irregularities that had motivated the search. Something was off. And as the decades passed and instruments improved, the picture of the outer solar system began to develop in ways that complicated the clean story everyone had been telling. In 1951, Gerard Kuiper suggested that the region beyond Neptune was the source of short-period comets, those with orbital periods of less than 200 years. This was a significant idea. Short-period comets had to come from somewhere relatively nearby in the solar system, because the long journeys from the far Oort cloud would not naturally produce the short, predictable orbits that these comets displayed. Kuiper proposed that there was a flattened disk of icy bodies just beyond Neptune, a reservoir, a warehouse of frozen material left over from the formation of the solar system, from which comets could be dislodged and sent sunward by gravitational nudges. The idea was elegant. It was also, for a long time, almost entirely theoretical. The objects in this proposed belt would be extraordinarily faint, small, dark, cold, and billions of miles away. The telescopes of the 1950s and 1960s had no hope of seeing them. And so the Kuiper belt, as it would eventually come to be named, existed for decades as a theoretical construct, a predicted population, a ghost in the equations. More detailed conjectures about objects in the belt were developed by Al G. W. Cameron in 1962, Fred L. Whipple in 1964, and Julio Fernandez in 1980. Each researcher added detail, refined the predictions, and extended the theory. And then, in 1992, the ghost became real. That year, astronomers David Jewett of the University of Hawaii and Jane Liu of UC Berkeley, working with the University of Hawaii's 2.2-meter telescope atop Mauna Kea in Hawaii, confirmed the observational proof of the Kuiper belt when the first member of this population beyond Pluto and Charon, 15,760, Albion, designated 1992 QB1, was found. It was a small reddish object orbiting beyond Neptune, and its discovery was, in the understated language of science, a significant result. Here was the first concrete evidence that the solar system's outer edge was not Pluto. Here was the first member of a population that Kuiper and Edgeworth and Fernandez had predicted, a population that would, in the years and decades that followed, proved to be far more extensive and far more diverse than any of them had imagined. The discoveries cascaded after that. In the 1990s and 2000s, improved survey telescopes began to find Kuiper belt objects at a rate that transformed the field. Dozens became hundreds. Hundreds became thousands. The picture that emerged was of a vast, flattened ring of icy material extending from just beyond the orbit of Neptune, roughly 30 astronomical units from the Sun, where 1 astronomical unit is the distance between Earth and the Sun, about 93 million miles, outward to somewhere around 50 astronomical units. The belt was populated by objects ranging from tiny fragments of ice and rock to bodies hundreds of kilometers across. It contained dwarf planets. Pluto, yes, but also Eris and Makemake and Haumea and Quaoar, worlds in their own right, with their own geology and, in some cases, their own moons. And at the heart of all this new discovery was an old question made fresh. What, exactly, are these things? Where did they come from? What do they tell us about the early solar system? The textbook answer, at least as it stood through most of the early 2000s, was relatively straightforward. The Kuiper belt was a remnant disk, material that had never managed to accrete into a full planet because Neptune's gravitational influence kept stirring the pot, preventing the gradual sticking together that had built the planets closer to the Sun. The objects in the belt were therefore primitive, ancient material, relatively unchanged since the solar system formed, but they were the leftovers of a failed process, not the products of a successful one. But here's what almost nobody tells you about that picture. It was already creaking under the weight of new evidence by the time most people learned it. The real story of where these objects came from and what they represent turned out to be far more complex, far more dynamic, and far more informative than the simple, failed planet belt narrative ever suggested. To see why, you need to understand something about the way the solar system formed, and how that formation process left its fingerprints all over the objects drifting in the dark beyond Pluto. Wind the clock back 4.5 billion years. The Sun does not yet exist. What exists is a vast, slowly rotating cloud of gas and dust, mostly hydrogen and helium, the basic currency of the universe, but laced with trace amounts of heavier elements forged in the nuclear furnaces of earlier stars. Carbon, oxygen, silicon, iron, water, ice, methane, ammonia, all the ingredients in the right proportions to eventually build planets and oceans and living things. Something disturbs this cloud, a nearby supernova perhaps, a shock wave moving through the interstellar medium, and the cloud begins to collapse under its own gravity. As it collapses, it spins faster, like a figure skater pulling in their arms. Most of the mass falls toward the center and ignites, the Sun, but not all of it. A thin, flat disk of gas and dust remains orbiting the newborn star, the protoplanetary disk, the raw material from which everything else in the solar system will be built. In the inner part of this disk, where temperatures are high, the lightweight gases are blown away by the young Sun's radiation. What remains is rocky material, and it begins to clump together. Dust grains stick to form pebbles. Pebbles accumulate to form boulders. Boulders crash into each other, and the survivors grow into planetesimals, kilometer-scale objects with enough gravity to attract more material. Over millions of years, this process, called accretion, builds the 4 rocky inner planets. In the outer part of the disk, beyond what astronomers call the frost line, the distance from the Sun at which water and other volatiles can remain frozen, the process works differently. Here, there is far more solid material available because the ices can contribute mass. planetesimals form quickly and grow large. And when they grow large enough, their gravity begins to capture the surrounding gas as well, producing the enormous gas and ice giant planets: Jupiter, Saturn, Uranus, Neptune. Now here is where the history of the solar system gets complicated, and where the Kuiper belt enters the story in a way that most textbooks have only recently begun to acknowledge. The giant planets did not form where we find them today. The evidence for this is overwhelming and comes from multiple independent lines of inquiry, from the architecture of the Kuiper belt itself, from the distribution of impact craters on the Moon, from computer simulations of planetary dynamics, and from comparisons with planetary systems around other stars. The giant planets formed closer to the Sun than their current positions and then migrated outward through a complex gravitational dance that unfolded over hundreds of millions of years. This migration had consequences. As Neptune moved outward, it swept through the region where the Kuiper belt now sits, gravitationally scattering objects, some inward toward the Sun, some outward into more distant orbits, some into the Oort cloud, and some captured into specific resonant relationships with Neptune's own orbit. The Kuiper belt we see today is not the original belt. It is the survivor of a violent reshuffling. It is a population that has been sorted, scattered, and sculpted by billions of years of gravitational interactions with the most massive planets in the solar system. This understanding, developed through the work of Renu Malhotra at the University of Arizona in the 1990s, through the NICE model developed by Alessandro Morbidelli and colleagues in 2005, and through subsequent refinements by dozens of researchers, fundamentally changed the way planetary scientists think about the outer solar system. The Kuiper belt is not just a debris field. It is a fossil record. It is a stratigraphic layer in the history of solar system evolution, and reading it correctly requires understanding not just what is there, but what is no longer there. The objects that were scattered away and the gravitational forces that scattered them. This is the foundation on which everything that follows rests. The strange things NASA found beyond Pluto are strange precisely because they do not fit the simple debris field picture. They fit a much richer, much more dynamic, much more revealing story. A story that begins with a small spacecraft launched from Cape Canaveral on a January morning in 2006, and a target so far away that it would take 9 years to reach. Take stock of where we are. We have established that the Kuiper belt is real, that it is populated by ancient and largely pristine remnants of the early solar system, and that its structure carries information about the violent dynamical history of the giant planets. We have established that the objects there are not the simple leftovers of a failed planetary formation process, but are instead witnesses to a solar system that was far more chaotic and dynamic in its youth than its current orderly appearance suggests. What we have not yet done is go there. What we have not yet done is close the distance between our telescopes and these ancient worlds, and see them not as points of light on a survey image, but as places, with geology, with chemistry, with shape and color and surface features that tell specific stories about specific events in the deep past. That journey begins with new horizons, and it begins, as all the best journeys do, with something unexpected. The New Horizons spacecraft is, by any reasonable measure, an extraordinary machine. It is roughly the size and shape of a grand piano, about the mass of a large motorcycle, just over 400 kilograms, and it carries within its compact frame 7 scientific instruments designed to do something no instrument had ever done before: examine their outer solar system from the inside. Not from a telescope on Earth or in Earth orbit, looking outward across billions of miles of intervening space, but from within the region itself, moving through it, sampling its dust and plasma and radiation, pointing cameras at objects that no camera had ever approached. New Horizons launched on January 19, 2006, from Cape Canaveral, Florida, aboard an Atlas V rocket. It left Earth at a speed of 36,000 miles per hour, faster than any spacecraft had ever been launched from Earth at the time of its departure. Even at that speed, it would take 9.5 years to reach its primary target. The scale of that journey is worth sitting with. 9.5 years of continuous travel, covering roughly 3 billion miles, to reach a world that occupies a point of light so faint that the Hubble Space Telescope had difficulty resolving it. The primary target, of course, was Pluto. And the story of what New Horizons found at Pluto, the towering mountains of water ice, the vast nitrogen glacier shaped like a heart, the evidence of ongoing geological activity on a world that should, by any conventional reckoning, have been geologically dead for billions of years, is itself a complete and astonishing story. But for our purposes, the Pluto encounter on July 14, 2015, was not the end of the mission. It was the beginning of a second act. After the Pluto flyby, New Horizons continued moving outward. It had enough fuel and enough power to keep operating for decades, and NASA's scientists had always intended to send it deeper into the Kuiper belt, toward a second target. The challenge was finding that target. The spacecraft's fuel budget was limited, which meant the next target had to be somewhere along its existing trajectory, a narrow corridor through space that constrained the search enormously. The search was led by astronomer Mark Buoy of the Southwest Research Institute, who, together with the New Horizons search team, used the Hubble Space Telescope in 2014 to examine this narrow corridor in extraordinary detail. Arakoth was discovered on June 26, 2014, by astronomer Mark Buoy and the New Horizons search team, who had been using the Hubble Space Telescope to find Kuiper belt objects that New Horizons could visit. Overall, these efforts resulted in the discovery of 85 Kuiper belt objects, including 11 that became objects for distant observation by New Horizons and Arakoth, which became the first post-Pluto flyby destination. The object that would become known as Arakoth was not much to look at in those initial Hubble images. It was a faint smudge, a point of light barely distinguishable from the background stars. But it was there, and it was reachable, and it was, according to the orbital calculations, a cold classical Kuiper belt object, which made it scientifically extraordinary. Cold classical Kuiper belt objects occupy a special place in planetary science. They are bodies that have remained in nearly circular, low-inclination orbits since the early solar system. Orbits that have been disturbed very little by Neptune's gravitational influence. They are, in this sense, the most pristine remnants available for study. They are the objects least changed from the original protoplanetary disk. One of the class of bodies called cold classical Kuiper belt objects, Arakoth is an ancient relic preserved from the time when the planets first began to form nearly 4.5 billion years ago. At 12:33 a.m. Eastern Time on January 1st, 2019, New Horizons flew just 2,200 miles, 3,500 kilometers, from the object's surface when it was about 4 billion miles, or 6.6 billion kilometers, from the Sun, the most distant planetary flyby in history and the first close-up look at a solar system object of this type. What the spacecraft saw changed everything. Before Arakoth, astronomers had two competing theories for how small bodies in the Kuiper belt formed. The first was the classical accretion model, the same basic mechanism responsible for building the inner planets, in which objects grew gradually through billions of individual collisions, each one adding a small amount of mass to a growing body. In this model, the early solar system was a chaotic demolition derby, and the survivors were the objects tough enough and lucky enough to absorb more impacts than they lost material to. This model predicted certain things about the shapes and surface features of the resulting objects. Specifically, it predicted irregular, battered shapes and heavily cratered surfaces, bearing the scars of the violent collisions that had built them. The second model was called streaming instability, or more specifically, the gravitational collapse model. In this scenario, small particles in the protoplanetary disk did not accumulate one by one through individual collisions. Instead, under the right conditions, concentrations of solid particles within the disk became locally dense enough to collapse under their own gravity, much the way a gas cloud collapses to form a star. The resulting objects would form quickly, over thousands rather than millions of years, and they would form gently without the violent collisions of the classical model. They would be relatively pristine, lightly cratered, and they would often form as binary pairs, two objects forming from the same collapsing cloud, orbiting each other, and eventually, if they were close enough and their orbits aligned correctly, drifting slowly together and touching. These two models made different predictions. The question was, which one was right? And Arakoth settled the argument. Arakoth is a contact binary, a snowman-shaped object composed of two lobes connected by a narrow neck of material. The lobes, named Wenu and Wio, are believed to be former planetesimals that once formed a binary system but gently merged together. Wenu and Wio have flattened shapes consisting of distinct mounds, which indicate that they formed from a collection of smaller planetesimals 4.5 billion years ago. The word gently in that description is doing enormous work. It is the word that distinguishes one theory from another, one understanding of planetary origins from another. If Arakoth had formed through violent collisions, its lobes would show evidence of high-speed impacts, fractures, compression features, asymmetrical deformation. Instead, its lobes are smooth, flattened, lightly cratered, and remarkably intact. They came together slowly, almost tenderly, as if they had been drifting toward each other for millions of years, and finally, inevitably, touched. With 10 times as much data and many months of computer modeling, the researchers saw a different story, one that involves Arakoth forming much more placidly. There are 5 different lines of evidence for cloud collapse, said Alan Stern, all pointing to the gentler formation theory. And if Arakoth formed that way, it is a sign the rest of the solar system's building blocks may have also emerged from a cloud of dust, rather than from the violent collisions of countless objects. 5 independent lines of evidence. That phrase deserves attention. In science, a single line of evidence is suggestive. 2 are compelling. 5 are, in the careful language that scientists use when they are trying not to appear too excited, decisive. New Horizons principal investigator Alan Stern, a planetary scientist at the Southwest Research Institute, reflected, "I never expected that our encounter with Arakoth would be shoulder to shoulder with the Pluto flyby in terms of its importance. I didn't expect to make an earth-shattering discovery about planet formation in the Kuiper belt, and yet we have. At Arakoth, we stumbled onto maybe the biggest prize of the entire New Horizons mission." That prize was not merely the solution to a debate between 2 formation models. It was a window into the very first moments of solar system history, a glimpse of a process that had been operating 4.5 billion years ago, preserved in the shape and surface of a 35-kilometer snowman, drifting in the cold dark beyond the reach of most instruments. The shape of Arakoth supports a theory of Kuiper belt object formation, where objects in the early solar system formed rapidly from the collapse of a local region of dust, and often formed two binary objects revolving around one another. This matters not just for our solar system, but for the thousands of planetary systems we are discovering around other stars. If our solar system's small bodies formed through gravitational collapse rather than collision-driven accretion, then the same process likely operated in other protoplanetary disks as well. And the architecture of those systems, the distribution and composition of their small bodies, would follow similar patterns. But Arakoth's most astonishing revelation is not its shape. It is its color. Picture the surface of Arakoth. You are hovering above it, perhaps 1,000 kilometers up, and the sun is so far away that it gives roughly 900 times less light and heat than it gives on Earth. A dim, cold star, barely brighter than the background of space. In this faint illumination, the surface of Arakoth glows a deep, uniform red. Not the red of rust or clay. Something darker, richer, more organic? The color of dried blood, or of the darkest red wines, or of old wood stained by decades of varnish. New Horizons found that the surface of Kuiper belt object Arakoth is uniformly coated by red-colored methanol ice. Since methanol ice usually is white, the origin of this red color was a mystery. That mystery is deeper than it first appears. When astronomers talk about red objects in the outer solar system, they are generally referring to the presence of complex organic molecules called tholins. Molecules formed when simple ices like methane, nitrogen, and water are bombarded by cosmic radiation over billions of years. The radiation breaks apart the original molecules and rearranges their fragments into increasingly complex chains and rings of carbon and hydrogen and nitrogen, building structures of growing complexity. Tholins are not alive, but they are the raw material, the building blocks of a building block, from which amino acids and nucleotides and all the other molecules of biology can be assembled under the right conditions. The uniform reddish color of Arakoth's surface is a direct record of 4.5 billion years of cosmic radiation processing the primordial ices that have sat on this object since before the Earth existed. Every photon of ionizing radiation, every cosmic ray proton from a distant supernova, every energetic particle streaming outward from the sun, all of them have been doing chemistry on Arakoth's surface for 4.5 billion years. What you see in that deep red color is the cumulative product of the oldest ongoing chemical experiment in the solar system. And because both lobes of Arakoth share this identical color, the albedo of Arakoth's two lobes provides an important clue to the object's origin, indicating that the parts formed at the same time or evolved together. The color itself is a confirmation of the formation story. Objects that had formed separately and come together violently would likely have different surface histories, different degrees of irradiation, different colors. But Wenu and Weo are the same shade of ancient red. They were always together in the same part of the protoplanetary disk, bathed in the same radiation environment, processed by the same 4.5 billion years of cosmic chemistry. This is the first of several moments in what follows, where you should allow yourself to feel the weight of the number 4.5 billion years. It is not a number that the human mind handles gracefully. Our intuitions about time extend comfortably to lifetimes, perhaps to centuries, with effort to millennia. 4.5 billion years is a number we can write and recite, but cannot truly inhabit. And yet, it is the number that underlies almost everything interesting about the Kuiper belt. The objects there are not just old in the way that ancient ruins are old. They are old in the way that the atoms in your body are old. assembled in the first generation of stars, incorporated into the solar nebula, pressed into planetesimals, and then left undisturbed in the dark for a span of time that encompasses the entire history of complex life on Earth many times over. Now we turn to a structural feature of Arakoth that has received less popular attention than its color or its snowman shape, but which carries perhaps the most information about the very earliest moments of solar system formation. Through continued analysis of New Horizons images, science team members have produced a new three-dimensional shape model of Arakoth. The model refines the overall structure, finding that the lobes are somewhat fatter than previously estimated, and that the volume ratio between the large and small lobes is close to 2:1. This new model highlights more of Arakoth's detailed structure, including some previously unresolved features such as indentations and hills superimposed on the lobes. One unique result is that the circular structure on the large lobe appears to be a broad mound rather than a depression, further indicating that it may have been an original component of Arakoth, rather than a large impact or later geologic feature. Read that last sentence carefully. The most prominent circular feature on Arakoth, the feature that initially looked like an impact crater, the feature that in the first images seemed to be a depression, is actually a mound, a protrusion. Not something that hit Arakoth from the outside, but something that was always part of it, a primordial structure formed when the original cloud of material collapsed and consolidated. This distinction between a scar left by a violent impact and a shape inherited from the original formation process is the distinction between a world that has been heavily modified since its birth and a world that still looks approximately as it looked when it first solidified from a cloud of dust and ice. Arakoth belongs to the second category. It is, as far as anyone can determine, nearly unmodified. It is a relic, a primary source, a document written 4.5 billion years ago in the language of ice and organic chemistry, sitting in the cold dark beyond Pluto, waiting for something with eyes to arrive and read it. There is, of course, a potential catch. Arakoth is the only object of its kind ever seen close up, and making enormous extrapolations from a sample size of one is inherently risky. This is the kind of intellectual honesty that separates good science from motivated reasoning, and it deserves respect. The researchers who made these discoveries are the first to acknowledge that one object, no matter how pristine and informative, is one object. The conclusions it supports are strong, but not absolute. They are the best current interpretation of the best currently available evidence, and that interpretation will be tested, refined, and possibly overturned as more data accumulates. But even with that caveat in place, Arakoth represents a pivot point in planetary science. These studies provide a far more complete picture of the composition and origin of Arakoth, and decisively shift the long-standing scientific debate about how planetesimals, the primordial building blocks of our solar system's planets, were formed. Current evidence strongly favors the gentle gravity collapse model for this object, and by inference, likely for the broader class of cold classical Kuiper belt objects that share its orbital characteristics. Research continues, and future flybys would be needed to confirm whether what we see in Arakoth is truly representative. What remains now is the question of what else is out there. Arakoth is one object, the one object New Horizons was able to reach. But the Kuiper belt contains hundreds of thousands of objects, possibly millions. What do we know about the broader population? What did the surveys and telescopes find when they turned their attention to the belt as a whole? And here is where the story takes its first unexpected turn. Because when astronomers began cataloguing the Kuiper belt in earnest, They found not a gradually fading distribution of objects stretching outward to some smooth boundary, but a sharp, inexplicable edge. A cliff in the data, a place where the population simply stops. Everyone who studied the Kuiper belt in the 1990s and early 2000s expected the same thing from its outer boundary. Based on theoretical models of how much solid material was available in the protoplanetary disk at various distances from the Sun, the predictions were consistent. Beyond 50 astronomical units, the number of Kuiper belt objects should increase. There should be more material farther out, or at least as much, because the disk of the early solar system extended far beyond that distance. What the surveys found instead was the opposite. Based on estimations of the primordial mass required to form Uranus and Neptune, as well as bodies as large as Pluto, earlier models of the Kuiper belt had suggested that the number of large objects would increase by a factor of 2 beyond 50 astronomical units. So this sudden drastic fall-off, known as the Kuiper cliff, was unexpected, and to date its cause is unknown. Read that final clause again. To date, its cause is unknown. This is not a minor puzzle. This is a gap in our understanding of the solar system's most basic architecture. The Kuiper belt, which should theoretically extend smoothly outward from Neptune's orbit to much larger distances, simply stops at approximately 50 astronomical units. The density of objects drops precipitously. The surveys find almost nothing beyond that boundary. The theoretical models predicted a gradual fade. The data shows a cliff. The Kuiper cliff refers to a sudden drop in the density of objects beyond Neptune in the Kuiper belt. The Kuiper belt is a region in our solar system that holds icy bodies and dwarf planets like Pluto. The cliff is marked by a noticeable decrease in the number of objects as you move farther from Neptune. This sudden drop has puzzled astronomers since its discovery in the 1990s. Several explanations have been proposed over the years. Some researchers think the cliff marks a genuine edge, a place where the protoplanetary disk simply ran out of material. Others think it reflects a gravitational resonance boundary, a place where Neptune's influence has cleared out objects over billions of years of orbital sculpting. Still others invoke the hypothetical presence of a large, undiscovered planet in the outer solar system, a body massive enough to have sculpted the distribution of Kuiper belt objects into the pattern we observe. This last hypothesis, the Planet 9 hypothesis, developed in detail by Mike Brown and Konstantin Batygin at Caltech in 2016, remains actively debated and unconfirmed. But here is where the story becomes genuinely strange. Because in the years since the Kuiper cliff was first noticed, something has been emerging from the data, something that the cliff hypothesis did not predict, and that changes the entire framework of the discussion. The cliff may not be a cliff at all. It may be the edge of a gap, a valley between two populations, the familiar inner belt, and a second, more distant belt lurking in the darkness beyond. A discovery published in the Planetary Science Journal suggests the Kuiper cliff is not a sharp cutoff and may even hint at a ring of more distant objects beyond the Kuiper belt. Deeper observations using the Hypersuprime cam on board the Subaru telescope commenced in 2020, uncovering 239 objects by 2023. The majority of these objects discovered with the Hypersuprime cam are within 30 to 55 astronomical units from the Sun, thought to be within the Kuiper belt. However, an additional cluster of 11 objects in the 70 to 90 astronomical unit region was also apparent, separated by a valley at 55 to 70 astronomical units. This valley has not been reported in previous observations. This hints toward a new population of Kuiper belt objects at 70 to 90 astronomical units. 11 objects, in a region where the models predicted almost nothing. 11 objects sitting beyond the cliff, separated from the main belt by a gap of 15 to 20 astronomical units, roughly 1.5 billion miles of relative emptiness. And here is the crucial piece of context. Our solar system's Kuiper belt long appeared to be very small in comparison with many other planetary systems. But our results suggest that idea might just have arisen due to an observational bias, said Wes Fraser of the National Research Council of Canada, a co-investigator on the New Horizons mission science team and the study's lead author. Observational bias, two words that carry enormous freight in science. The Kuiper belt looked small because our instruments could not see the faint, distant objects that populate its outer reaches. The cliff was not a cliff. It was the edge of our vision. And then, almost simultaneously with these telescope discoveries, New Horizons itself weighed in with evidence from an entirely different kind of measurement. Not images of individual objects, but the dust between them. Picture yourself as a particle of frozen debris the size of a grain of sand, drifting between Kuiper belt objects 50 astronomical units from the Sun. You are the product of a collision. Two larger icy bodies struck each other at some point in the recent past, geologically speaking, and shed material. And you are a fragment of that shed material, tumbling slowly through the cold dark. You are too small and too faint for any telescope to detect. But you are there, and you are not alone. There are countless others like you, a thin haze of microscopic wreckage permeating the space between the larger objects. New Horizons carries an instrument called the Venetia-Burney Student Dust Counter, named for the 11-year-old English schoolgirl who in 1930 suggested the name Pluto for the newly discovered object. The instrument is essentially a very sensitive collision detector, a set of piezoelectric panels that produce a measurable electrical signal when a dust particle strikes them. By counting these signals and measuring their intensity over time, the instrument builds up a picture of how the density of dust changes with distance from the Sun. The first science instrument on a NASA planetary mission to be designed, built, and flown by students, the Student Dust Counter counts and measures the sizes of dust particles, producing information on the collision rates of such bodies in the outer solar system. The expectation, based on the models that predicted a sharp Kuiper cliff, was straightforward. As New Horizons moved beyond 50 astronomical units, the dust density should drop sharply. The cliff in the object counts should be mirrored by a cliff in the dust counts. Fewer objects means fewer collisions, means less dust. The models were specific and quantitative. The Student Dust Counter instrument has continued to measure dust along the New Horizons trajectory beyond 50 astronomical units during the extended missions. Surprisingly, the amount of dust measured has remained at a high value, despite model predictions that the dust flux would start to decline in these distant parts of the solar system. Not a small discrepancy, not a 10 or 20% shortfall that might be explained by instrument calibration or model uncertainty. Speeding through the outer edges of the Kuiper belt, almost 60 times farther from the Sun than Earth, the New Horizons Venetia-Burney Student Dust Counter instrument is detecting higher than expected levels of dust. The tiny frozen remnants of collisions between larger Kuiper belt objects and particles kicked up from KBOs being peppered by microscopic dust impactors from outside of the solar system. The readings defy scientific models that the Kuiper belt object population and density of dust should start to decline 1 billion miles inside that distance and contribute to a growing body of evidence that suggests the outer edge of the main Kuiper belt could extend billions of miles farther than current estimates. or that there could even be a second belt beyond the one we already know. A second belt. The phrase sits in the scientific literature with a quiet radicalism that is easy to miss if you are not paying attention. A second belt beyond the one we already know would mean that our solar system's outer architecture is fundamentally different from what the standard models describe. It would mean that the solar system has a hidden second ring of primordial material, an entire belt of ancient ice worlds that has been invisible to us, not because it is not there, but because it is too far away, too faint, and too cold to have appeared in the surveys we had the technology to conduct. Alex Donor, a physics graduate student at the University of Colorado Boulder, who serves as student dust counter lead, summarized. New Horizons is making the first direct measurements of interplanetary dust, far beyond Neptune and Pluto, so every observation could lead to a discovery. The idea that we might have detected an extended Kuiper belt, with a whole new population of objects colliding and producing more dust, offers another clue in solving the mysteries of the solar system's most distant regions. Every observation could lead to a discovery. That sentence is not merely enthusiastic science communication. It is a precise description of what it means to be operating an instrument in a region of space that no instrument has ever occupied before. New Horizons is not merely the farthest operational spacecraft. It is the only spacecraft ever to have made in situ measurements in the Kuiper belt, the only instrument to have been physically present in this region, surrounded by the objects it is studying, rather than observing them from a distance. Its data is, by definition, unique. There is nothing to compare it to. Every reading is a first. New Horizons scientists, using observatories like the Japanese Subaru telescope in Hawaii, have also discovered a number of Kuiper belt objects far beyond the traditional outer edge of the Kuiper belt. This outer edge, where the density of objects starts to decline, was thought to be at about 50 astronomical units, but new evidence suggests the belt may extend to 80 astronomical units, or farther, 80 astronomical units. This is more than 7 billion miles from the Sun. This is a region of space so remote that the Sun, seen from there, would appear as nothing more than the brightest star in the sky. Not a disk, not a source of warmth, just a very bright point of light, cold and distant. And in that cold and distant darkness, according to the converging evidence from New Horizons' dust counter and the Subaru telescope survey images, there are objects, there are icy worlds, there is structure. The solar system is larger than we thought. It was always larger than we thought. It just required a spacecraft bold enough to keep moving and instruments sensitive enough to notice what the darkness was whispering back. Stand at the edge of what we know and look outward. Not with instruments, not with theory, but with the simple willingness to hold uncertainty, to recognize that the map drawn by a century of astronomy has, in the last decade, been extended at its outer margins in ways that nobody predicted and that nobody yet fully understands. The evidence is real. The data is in. But the interpretation is still being assembled, piece by careful piece, by researchers working at the limits of what current technology can see. This is where science lives, not in the settled answers, but in the actively contested questions, the places where 2 or 3 different explanations are all consistent with the available data, and where the next observation, the next instrument, the next flyby, might be the one that finally distinguishes between them. The question of what lies beyond. The traditional Kuiper belt boundary, what occupies the space between 50 and 90 astronomical units, and whether the objects found there constitute an extension of the known belt or a genuinely distinct second population, is one of those actively contested questions. And to approach it with the depth it deserves, you need to understand something about the different families of objects within the Kuiper belt itself. Because the belt is not a single uniform population. It is a collection of distinct dynamical families, each with its own history, its own chemistry, and its own relationship to the violent gravitational reshuffling of the early solar system. The vocabulary of Kuiper belt science can be initially daunting, but the underlying structure is elegant once you see it. The objects in and beyond the Kuiper belt fall into several broad categories, and the categories reflect genuine physical and historical differences. The first and most familiar category is the resonant objects. Kuiper belt objects locked into precise gravitational resonances with Neptune. Pluto is the most famous example. It orbits the Sun exactly twice for every 3 Neptune orbits, a 2-to-3 resonance that has kept Pluto in a stable, predictable relationship with Neptune for billions of years, protecting it from the chaotic gravitational scattering that might otherwise have ejected it from the solar system entirely. There are thousands of objects in this resonance, and they are called Plutinos in Pluto's honor. Other resonances, 3-to-5, 4-to-7, 1-to-2, trap different populations of objects at specific distances, creating rings within the belt where object density is higher than in the spaces between resonances. The second category is the cold classical objects, the population to which Arakoth belongs. These are objects in nearly circular low-inclination orbits between approximately 42 and 48 astronomical units, with orbital characteristics suggesting they have been disturbed very little since the solar system formed. The word cold here does not refer to temperature. Everything in the Kuiper belt is extraordinarily cold, hovering around -230 degrees Celsius. It refers to orbital velocity dispersion. Cold classical objects have orbits that are all moving in roughly the same direction at roughly the same speed, like cars on a highway where everyone is going the same pace. They are cold in the sense that a gas is cold when its molecules are not moving rapidly relative to one another. The cold classicals are scientifically precious precisely because of this dynamical coldness. Their orbits have not been heated, stirred up, scattered, randomized by gravitational interactions with Neptune. They have sat in their quiet, circular orbits since the protoplanetary disk era. They are the least disturbed, most pristine material available for study in the solar system. And they tend to be red, that deep, Tholin's-rich red. And they tend to occur in binary pairs at a remarkably high rate, which is itself evidence for the gentle gravitational collapse formation mechanism that Arakoth confirmed. The third category is the hot classical objects. Confusingly named, these are Kuiper belt objects in orbits that are more elliptical and more inclined than the cold classicals. Their orbital heat, the randomness and spread of their velocities, indicates that they have been gravitationally stirred, likely during Neptune's outward migration. They are generally less red than the cold classicals, with more neutral or bluish colors on average, and they show less tendency to occur as binaries. They represent material that was scattered and resettled into the Kuiper belt region after Neptune's migration, rather than material that was always there. The fourth category is the scattered disk, objects in highly eccentric orbits that take them from within the Kuiper belt out to extremely large distances at their farthest points. These are bodies that received gravitational kicks from Neptune or the other giant planets and have orbits that reflect that violent history. Eris, the dwarf planet whose discovery in 2005 triggered the demotion of Pluto, is a scattered disk object. So is Sedna, a mysterious body discovered in 2003 by Mike Brown, Chad Trujillo, and David Rabinowitz, that has a remarkably elongated orbit, taking it from 76 astronomical units at its closest. Approach to roughly 937 astronomical units at its farthest. Sedna's orbit is so extreme that no known planet can explain it, which is one of several lines of evidence that originally motivated the Planet 9 hypothesis. And then there is the fifth category, the most recently and incompletely defined, which might be called the extended scattered disk, or the distant population, or simply the objects beyond the cliff. These are the bodies that have been appearing in surveys like the Subaru Hypersuprime Cam observations. Objects at 70 to 90 astronomical units, occupying the space that was supposed to be nearly empty, suggesting that what we called the Kuiper belt's outer edge was really just the limit of our vision. Understanding these families matters because each family carries different information. The cold classicals tell you about the original protoplanetary disk, the state of the outer solar system before the giant planets migrated. The hot classicals and resonant objects tell you about Neptune's migration itself, the dynamics of the reshuffling. The scattered disk tells you about the violence of the giant planet era, the gravitational storms that sent objects careening to extreme distances. And the distant population, if it is real and if it constitutes a distinct belt, tells you something that none of the other families tell you clearly: that the solar system's outer architecture extends much farther than expected, and that the protoplanetary disk itself was either much more extended than standard models suggest, or that some dynamical process has moved material from its original location to these remote orbits. Some researchers think the distant population is the outer extension of the classical belt, that it was always there, just invisible to surveys of insufficient depth. Others think it represents a genuinely distinct second belt, perhaps analogous to the structural features seen in the debris disks around other stars. A new discovery published in the Planetary Science Journal suggests the Kuiper Cliff is not a sharp cutoff, and may even hint at a ring of more distant objects beyond the Kuiper belt. Both interpretations are currently consistent with the data. The question will be resolved, slowly, patiently, as deeper surveys accumulate more objects in this region and allow statistical analysis of their orbits, colors, and sizes. This is the kind of uncertainty that feels frustrating from the outside, but is, from the inside of the science, immensely exciting. The data is pointing at something real. The shape of what it is pointing at is still coming into focus. Now we turn to the question of composition, what these objects are actually made of at the molecular level. Because the Kuiper belt is not just a collection of icy bodies whose interest lies in their orbital dynamics. It is a chemical archive. And the recent arrival of the James Webb Space Telescope has opened that archive in ways that were simply not possible before. JWST's approach to Kuiper belt science exploits the telescope's extraordinary sensitivity at infrared wavelengths, the range of light beyond the red end of the visible spectrum, where molecules absorb and re-emit energy in patterns as distinctive as fingerprints. When infrared light from the sun reflects off the surface of a Kuiper belt object, specific molecules in the surface absorb specific wavelengths, producing dips in the reflected spectrum. By measuring these dips with precision, astronomers can identify which molecules are present in the surface ice and in what abundances. Before JWST, this kind of spectroscopy was possible only for the largest and brightest Kuiper belt objects, Pluto, Eris, Makemake, Haumea, because smaller objects simply did not produce enough reflected light for existing instruments to analyze. JWST's collecting area and sensitivity push the boundary dramatically further, enabling compositional measurements for objects that were previously too faint to characterize. Using data obtained by Webb's near-infrared spectrometer, an international team of astronomers observed 3 dwarf planets in the Kuiper belt: Sedna, Gonggong, and Quaoar. These observations revealed several interesting things about their respective orbits and composition, including light hydrocarbons and complex organic molecules. The key point here is not merely what was found in any individual object, but what the diversity of findings reveals about the belt as a whole. JWST has also examined binary Kuiper belt objects with compositional spectroscopy, and the results have begun to reveal a taxonomic structure in surface chemistry that mirrors the dynamical structure of the belt itself. In a recent preprint from a team examining cold classical Kuiper belt binaries, JWST spectroscopy of a blue binary, cold classical Kuiper belt object, revealed striking compositional diversity even within the cold classical population. The measured reflectance spectrum of one object, designated 2001 XR254, is characteristic of the red cold classicals, with strong features due to carbon dioxide, carbon monoxide, and methanol ices. In contrast, 2016 BP81 is a blue binary with a water ice-rich surface composition. The 2 components of the 2016 BP81 binary display identical spectral profiles consistent with coeval formation from gravitational collapse. 2 binaries side by side in the cold classical belt with radically different surface compositions, one coated in carbon-rich organic ice, the other dominated by water ice. Through qualitative and quantitative comparisons of water ice-rich Kuiper belt objects observed with JWST, researchers have identified a small subclass, including 2016 BP81, that appears to differ in systematic ways from the rest of the population. The relatively deep carbon dioxide ice absorption bands and enhanced signatures of aliphatic organics suggest that objects within this subclass may have originated in a distinct formation environment from the other water ice-rich Kuiper belt objects. A distinct formation environment. 2 objects, visually similar, dynamically similar, separated by perhaps a few astronomical units in the early solar system, and yet chemically distinct enough to have formed in different parts of the protoplanetary disk before being brought together in their current location by the gravitational upheavals of the early solar system. The cold classical belt is not as cold and undisturbed as it first appeared. It too has been mixed, at least slightly, by the same dynamical processes that heated the rest of the outer solar system. This finding matters because it suggests that the chemical composition of Kuiper belt objects encodes information about where they formed in the protoplanetary disk, and that by reading those chemical fingerprints carefully enough, it may be possible to reconstruct the compositional gradient of the original disk, to map which molecules were present at which distances from the young sun, and to trace the journeys that individual objects made from their birthplaces to their current orbits. This is the kind of information that planetary scientists have been seeking for decades. It is the kind of detail that was impossible to access from Earth, barely accessible even from the Hubble Space Telescope, and only now becoming available through JWST's extraordinary sensitivity. And it is already revealing a complexity in the Kuiper belt's chemical architecture that the simple primordial frozen debris picture never anticipated. Consider the surface of a Kuiper belt object in detail, not just its color and composition, but the processes acting on it right now, in the present, at this moment. The outer solar system is not a static place. Even at temperatures approaching absolute zero, even at distances where sunlight is barely a whisper, the surfaces of Kuiper belt objects are being actively processed. The dominant surface modification process in the outer solar system is space weathering, a term that encompasses several distinct physical and chemical mechanisms. The first is solar wind irradiation, the constant stream of charged particles flowing outward from the sun strikes the surfaces of small bodies and implants energy, breaking chemical bonds and enabling new ones to form. At the distances of the Kuiper belt, the solar wind is much weaker than it is at Earth's orbit, but it has been acting continuously for 4.5 billion years, and the cumulative effect is substantial. The second mechanism is cosmic ray irradiation. Galactic cosmic rays, high-energy protons and heavier nuclei produced by supernovae and other energetic events throughout the galaxy, penetrate to greater depths than solar wind particles and do more energetic chemistry. They are particularly effective at converting simple ices to complex organics, building tholin layers that can extend tens of centimeters below the surface over geological timescales. The third mechanism is micrometeorite bombardment, the continuous rain of tiny particles from interstellar space and from within the solar system, each impact delivering a small pulse of kinetic energy that vaporizes surface material, mixes layers, and deposits new material. This is the process that the Venetia Burney student dust counter aboard New Horizons is detecting. Not the micrometeorites themselves, but the dust produced when they strike larger Kuiper belt objects and kick up debris. And the fourth mechanism, surprising and only recently appreciated, is the seasonal cycle driven by Pluto's own atmosphere and analogous processes on other large Kuiper belt bodies. Pluto has an atmospheric pressure cycle tied to its orbital eccentricity. At its closest approach to the Sun, the nitrogen ice on its surface sublimes into vapor, creating a thin atmosphere. At its farthest point, that atmosphere collapses back to the surface as frost. This cycle moves material around the surface, refreshing some regions, burying others, and creating the extraordinary patchwork of light and dark terrain that New Horizons revealed in such astonishing detail in 2015. New Horizons found that the large ice volcanoes it discovered on Pluto are unique in the solar system, geologically young and enigmatic. The discovery of cryovolcanism, volcanic activity driven by the eruption of molten ice rather than molten rock, on Pluto was one of the most surprising findings of the entire mission. The features involved, informally named Wright Mons and Piccard Mons, are enormous structures. Wright Mons is roughly as large as Hawaii's Mauna Loa in total volume. Built from water ice that erupted from Pluto's interior, with irregular, hummocky surfaces that bear no resemblance to impact craters. Cryovolcanism on Pluto suggests that there is internal heat available to drive geological processes on a world that has no radioactive heating comparable to Earth's, and that should, by naive calculation, have frozen solid billions of years ago. The source of this heat is not fully understood. Some researchers think residual heat from Pluto's formation is sufficient, stored in its rocky core and slowly leaking outward. Others invoke tidal interactions with Charon, Pluto's large moon, which dissipate energy in Pluto's interior through the flexing of tidal forces. Still others suggest that the crystallization of a subsurface ocean, the gradual freezing of liquid water beneath Pluto's ice shell, could release latent heat over geological timescales. All three mechanisms are plausible. None is definitively confirmed. But here is the genuinely profound implication. If Pluto, a body at the outer edge of the classical Kuiper belt, still has enough internal energy to drive cryovolcanism, active geological processes, then the assumption that small bodies in the outer solar system are geologically dead is wrong. The outer solar system may be geologically alive in ways that were not anticipated. Other large Kuiper belt objects, Eris, Makemake, Gonggong, Quawa, may harbor similar geological activity, and some may even have subsurface liquid water maintained by the same mechanisms operating on Pluto. Subsurface liquid water. At distances of 40, 50, 60 astronomical units from the Sun, in bodies that receive less than 1,000th of the solar energy available at Earth's orbit. The possibility is not merely interesting. It is, for anyone who cares about the distribution of habitable environments in the solar system, genuinely significant. Step back, briefly, and consider the broader picture that has been assembling itself across these first 3 deep dives into the Kuiper belt. We began with the simple discovery that the belt exists, a vast ring of primordial material beyond Neptune, theoretically predicted and observationally confirmed through decades of patient sky survey. We moved to the specific discoveries made by New Horizons at Arakoth, the shape that speaks of gentle formation, the color that records 4.5 billion years of cosmic radiation chemistry, the geological clarity that settles a long-standing debate about how planetary building blocks were made. We moved to the dust measurements that reveal the belt extends far beyond its supposed boundary, and to the telescope surveys that are beginning to detect individual objects in the gap region. And now we have reached the chemical complexity revealed by JWST's spectroscopy, a complexity that encodes the compositional gradient of the original protoplanetary disk and the dynamical history of the early solar system. Each layer has revealed a world more complex, more active, and more information-rich than the layer above it. Each answer has opened new questions. That is the characteristic pattern of mature scientific inquiry into a rich subject. Not a smooth march toward complete understanding, but a deepening, a branching, a proliferation of detail that opens faster than it closes. But there is one more layer to descend into before we reach the deepest and most recently discovered complexity. It is a layer that concerns not individual objects, not dust measurements, not surface chemistry, but the light itself, the faint glow of background radiation that New Horizons has been measuring from its unique vantage point in the outer solar system. And what New Horizons found in that measurement is, by any measure, one of the strangest results in contemporary astronomy. New Horizons recently obtained the best ever measurement of the light coming from the distant universe. An earlier 2021 analysis had suggested the level was roughly double that accounted for by all known galaxies, hinting at an unexplained anomalous component. But a 2024 follow-up analysis by the same team, using a larger survey of 16 high galactic latitude fields and a refined treatment of foreground diffuse galactic light, found that the cosmic optical background is in fact entirely consistent with the integrated light from all known galaxies. The anomalous excess that had once captivated cosmologists has, with better data, evaporated. Listen to that again. Double. Every galaxy astronomers have ever catalogued, every spiral, every elliptical, every irregular galaxy in the observable universe, counted, measured, their light carefully added up, produces only half the total background light that New Horizons detected when it pointed its cameras at a dark patch of sky from its position in the outer solar system. The measurement that produced this result exploits a capability unique to New Horizons' position. When you observe the night sky from Earth, your view of the cosmic optical background, the faint glow of light from all the distant galaxies in the universe, is contaminated by numerous sources of foreground light. The glow of the Milky Way, the scattered light of the zodiacal dust cloud, the atmospheric air glow, the light pollution of human civilization. Disentangling the true cosmic background from all these contaminants is enormously difficult, and the uncertainties in the result are large. From New Horizons' position in the outer solar system, several of these contaminants are dramatically reduced. The spacecraft is far enough from the Sun that the zodiacal dust cloud, a lens-shaped distribution of interplanetary dust particles that scatters sunlight and dominates the optical background from Earth's vantage point, is much fainter. And there is, of course, no atmospheric airglow and no light pollution. New Horizons' measurement of the cosmic optical background is therefore the cleanest ever made, the most accurate estimate of how much light is genuinely arriving at our solar system from the distant cosmos. And it is twice what the galaxy catalogues predict. The implications of this discrepancy divide the scientific community. Some researchers think the discrepancy reflects a genuine population of faint galaxies, objects too small, too faint, or too diffuse to appear in current galaxy surveys, that collectively contribute light equal to the total from all the currently catalogued galaxies combined. This would require an enormous hidden population of diffuse or low-surface brightness galaxies, an interpretation that some cosmologists find implausible given current understanding of galaxy formation. Others think the extra light comes from stars that have been stripped from their parent galaxies by gravitational interactions and now drift through intergalactic space as isolated stellar nomads, a population of intracluster stars that is invisible to most observations, but collectively produces a substantial background glow. The skeptics turned out to have a point. A 2024 reanalysis by the same New Horizons team, drawing on a wider survey and a substantially refined estimate of foreground diffuse galactic light, brought the measurement into agreement with the integrated brightness of known galaxies. The earlier suggestion of a doubled cosmic optical background did not survive better data. What remains, even after the anomaly faded, is the achievement itself. From its unique position in the outer solar system, New Horizons has made the most precise direct measurement ever obtained of the brightness of the universe. And the answer, as far as we can now tell, is that the light filling deep space comes from galaxies, and only from galaxies. The simplest interpretation, in Mark Postman's words, is that the cosmic optical background is completely due to galaxies. The mystery did not deepen. It closed. What is agreed upon is that the measurement exists, that it is the best measurement of its kind ever made, and that if it is correct, there is something significant missing from our census of the observable universe. New Horizons has made the most distant and most sensitive measurement of the brightness of space, and discovered there are no mysterious sources of this background glow, in the sense that no specific new source has been definitively identified. The mystery is clean. The data is real. The explanation is unknown. We cannot know, with current instruments and current methods, which of the proposed explanations is correct. This is not a statement of scientific failure. It is a statement about the genuine frontier of knowledge, the place where the evidence runs out before the understanding does, and where the only honest position is to say, something is there, something is producing this light, and we do not yet know what it is. New Horizons made one more unexpected observation in its extended mission that deserves careful attention, not because it is directly related to the Kuiper belt structure, but because it reveals something about the nature of the space through which the belt moves. New Horizons has made the first continuous measurements of ionized atoms arriving from outside the solar system across a wide swath of the heliosphere. These measurements trace the boundary between the solar system and interstellar space, the heliopause, where the solar wind meets the interstellar medium, and reveal it to be a more complex, more dynamic structure than previous measurements suggested. The heliosphere, the bubble of solar wind plasma that surrounds the Sun and extends to roughly 120 astronomical units or beyond, is not static. It breathes, in a sense, expanding and contracting in response to fluctuations in the solar wind and in the pressure of the surrounding interstellar medium. The Kuiper belt sits entirely within this heliospheric bubble, bathed in the solar wind, even at distances of 40 or 50 or 80 astronomical units. The interstellar medium, the thin gas and dust of the galaxy, cannot directly reach the Kuiper belt's objects. It is filtered, attenuated, and modified by the Sun's own magnetic field and wind before it arrives. New Horizons detected an unexpected and previously unexplained bump in pickup ion temperature over a 5-year period. Pickup ions are atoms from the interstellar medium that have been ionized by solar ultraviolet radiation and then swept up by the solar wind, which accelerates them to high energies. The temperature anomaly New Horizons detected in these ions does not fit existing models of how pickup ions should behave at the distances in question. Something is depositing energy into these particles, heating them in ways that the models do not predict. The energy source is unknown. The several proposed mechanisms, including wave-particle interactions, shocks in the solar wind, or inhomogeneities in the interstellar medium, each make different predictions about what further observations should find. New Horizons, as the only spacecraft in a position to measure these phenomena directly, will continue to accumulate data on this anomaly as it moves outward, and the pattern of how the temperature changes with distance will eventually discriminate between the competing explanations. But notice what is happening here. A spacecraft sent to photograph Pluto and a Kuiper belt snowman has become, in its extended mission, an instrument probing the physics of the heliospheric boundary, the population and distribution of Kuiper belt objects and their dust, the cosmic optical background, and the interstellar pickup ion population. It is, in effect, a Swiss Army knife of deep space exploration, doing science that nobody anticipated when it was designed and launched. This is the characteristic outcome of deep space exploration. The universe is more interesting than the specific question that motivated the instrument, and every journey into unknown territory returns with discoveries that were not on the itinerary. Return now to the surface of the Kuiper belt, not the abstract statistical surface of survey counts and dust measurements, but the physical surface of specific objects seen up close or characterized in detail. Because one of the most important things JWST is doing in the Kuiper belt is not just measuring individual objects, but beginning to build a compositional taxonomy, a map of how different types of surface chemistry correlate with different orbital families. The emerging picture is one of radical diversity within a seemingly uniform region. The Kuiper belt objects studied with JWST's near-infrared spectrometer range from objects dominated by pure water ice to objects with surfaces rich in methane and nitrogen, to objects coated in complex organic tholins, to objects that appear to have surface exposures of carbon dioxide ice, carbon monoxide ice, and methanol ice simultaneously. The largest objects, Pluto, Eris, Makemake, show the greatest compositional complexity, with different surface regions having detectably different compositions, reflecting their different histories of sublimation, condensation, and geological activity. Smaller objects tend towards simpler surface compositions, though even among the smaller cold classicals, the JWST data is revealing surprising diversity. The James Webb Space Telescope's program of Kuiper belt science is still ongoing. The initial reconnaissance of surface compositions is informing our understanding of the long history of processes in the outermost regions of the Sun's protoplanetary disk. That phrase, initial reconnaissance, is important. JWST has been operating in full science mode since 2022, and the Kuiper Belt program is in its early stages. The data accumulating from these observations will continue to be analyzed and published for years to come, and each new paper will add detail to a compositional map that is, at this moment, still mostly blank. Alongside JWST, the ground-based Vera C. Rubin Observatory in Chile, an 8.4-meter optical survey telescope coupled to a 3.2 gigapixel LSST camera, the largest digital camera ever built, is expected to revolutionize the discovery of new Kuiper Belt objects in a way fundamentally different from JWST, where JWST excels at characterizing the composition of known objects. The Vera C. Rubin Observatory will survey the entire sky repeatedly and rapidly, detecting thousands of new Kuiper Belt objects through their motion against the fixed stars. Its wide field of view and extraordinary sensitivity to faint, moving objects will extend the Kuiper Belt census dramatically, filling in the statistical picture of the belt structure, finding the objects in the gap region between 50 and 90 astronomical units, and potentially detecting the members of the proposed second belt, if it exists. One of those objects is Kuiper Belt objects that we don't yet know about. It's going to be a big new discovery tool. Within the next decade, the combination of JWST's spectroscopy and the Vera C. Rubin Observatory's survey power will produce a map of the outer solar system that makes current knowledge look as sketchy as a medieval cartographer's rendering of an unexplored continent. And threading through all of this, still moving, still transmitting, its instruments still gathering data in the cold and dark 5 billion miles from the Sun, is New Horizons. Currently in its extended mission, New Horizons is proving to be a resilient spacecraft with hopes of lasting well into the 2040s. The research team anticipates that given its current velocity, the spacecraft could reach up to 100 astronomical units from the Sun. The student dust counter might identify the transition point into interstellar space, providing invaluable data about the outermost regions of our solar system. 100 astronomical units. The boundary of the heliosphere, where the solar wind finally loses its grip on the local environment and the true interstellar medium begins. If New Horizons survives long enough to reach that boundary, the data it will collect will be unlike anything any instrument has gathered before. A direct in situ measurement of the transition from solar system to galaxy, the point where the Sun's influence ends and the wider cosmos begins. We are not there yet, but we are moving toward it at 36,000 miles per hour through a darkness that turns out to be less empty and far more extraordinary than anyone predicted. Pause here, because the next layer of the story requires a different kind of attention. Everything explored so far, the formation of Arakoth, the chemistry of Kuiper Belt surfaces, the dust measurements that suggest a second belt, the anomalous background light, has been building toward a question that sits at the center of the entire enterprise. It is not a question about any individual object or any single measurement. It is a question about the solar system's identity. How typical are we? Not in the philosophical sense, not the ancient question of whether our existence is unique or common in the cosmos, but in the structural, architectural sense. Does our solar system's outer region look like the outer regions of other planetary systems around other stars? Is the Kuiper Belt, this ancient ring of frozen primordial material, a standard feature of planetary architectures, or is it an oddity? And if it is an oddity, what does that say about the specific history of events that shaped our solar system's youth? These questions have been hovering at the edges of Kuiper Belt science since the first exoplanetary systems were discovered in the 1990s. And they have become urgently relevant in the last decade as the census of planetary systems around other stars has grown from dozens to thousands, And as the debris disks, the extrasolar analogues of the Kuiper belt, have been resolved and characterized in enough detail to make meaningful comparisons, the answer, emerging slowly from the accumulation of evidence, is one that should readjust your picture of where the solar system stands in the broader distribution of planetary architectures. And it begins with a fact that most popular accounts of the outer solar system never mention. The textbook version of the Kuiper belt is this. Our solar system has a Kuiper belt. It extends from about 30 to 50 astronomical units, and it contains a certain amount of mass distributed among hundreds of thousands of icy bodies. Compared to the debris disks seen around other stars, our Kuiper belt is relatively modest. A thin, low-density ring, not the bright, massive disks seen around young stars like Fomalhaut or Beta Pictoris. That apparent modesty has been interpreted for years as a sign of the solar system's maturity. Young planetary systems have massive, dusty disks because the collision rates between their small bodies are still high. The system has not yet had time to grind itself down, disperse its material, or clear its most dynamically unstable regions. As a planetary system ages, the collisional cascade reduces the mass in small bodies, the disk thins, and the system's debris disk fades to something as quiet and unobtrusive as our own Kuiper belt. But here's what that picture doesn't account for. It assumes that our Kuiper belt, as currently observed, is a fair sample of the total reservoir of small bodies in the outer solar system. It assumes that the belt we can see, the population of objects detectable with current survey capabilities, represents most of what is there. The discoveries of the last several years suggest that assumption is wrong. Our solar system's Kuiper belt long appeared to be very small in comparison with many other planetary systems, but our results suggest that idea might just have arisen due to an observational bias, said Wes Fraser of the National Research Council of Canada. Observational bias. If the Kuiper belt extends to 80 or 90 astronomical units, if there is a second population of objects at 70 to 90 astronomical units beyond the traditional edge, then the total mass of material in the outer solar system may be substantially larger than current estimates suggest. The apparent thinness of our Kuiper belt may simply be an artifact of the fact that we could only see the inner, brighter, closer part of it. The outer part, dimmer and more distant, was invisible to the surveys that defined our understanding of the belt's structure. This matters enormously for the comparison with other planetary systems. If our Kuiper belt is actually larger and more massive than we thought, if the true outer edge is at 80 or 90 or even more astronomical units rather than 50, then our solar system's debris disk may be more comparable to the disks around other stars than the standard picture suggests. Our solar system may be less anomalous than it appeared. Or, stated differently, the other planetary systems may be less exotic than they appeared. The common ground between our system and others may be larger than the truncated Kuiper belt picture implied. Both possibilities are scientifically rich. A solar system that turns out to be more typical than thought would strengthen the case for the universality of planetary formation processes, for the idea that the same basic mechanisms that built our solar system are building planetary systems around most stars. A solar system that turns out to be genuinely unusual in some specific way would raise the question of what specific early events, what particular gravitational dynamics, what specific sequence of giant planet migrations produced the outcome we observe here. We cannot know with certainty which is true. The data is not yet sufficient, but the direction of the evidence is clear. The solar system is larger and more complex and more comparable to other planetary systems than the simple picture suggested. The comparison with other planetary systems leads naturally to one of the most contentious and most consequential open questions in contemporary planetary science, the Planet 9 hypothesis. In January 2016, Mike Brown and Konstantin Batygin, both at the California Institute of Technology, published a paper in the Astronomical Journal proposing that the unusual orbital clustering of a group of distant trans-Neptunian objects, bodies in the scattered disk with orbits reaching to extreme distances, could be explained by the gravitational influence of a large undiscovered planet in the outer solar system. The proposed body, which they called Planet 9, would have a mass of roughly 10 times that of Earth, an orbit tilted roughly 30 degrees relative to the plane of the solar system, and an orbital period of about 15 to 20,000 years. At its farthest point from the Sun, it would be roughly 1,200 astronomical units away in the original 2016 estimate, though subsequent refinements by Brown and Batygin in 2019 and 2021 have shrunk both the mass and the orbit, suggesting a planet closer to 5 Earth masses on a smaller orbit with a period of about 10,000 years. Either way, the body would be so faint that most current telescopes would struggle to detect its reflected sunlight. The evidence for Planet 9 rests on the observed clustering of the perihelia, the closest approach points, of 6 extreme trans-Neptunian objects. These objects, with orbital periods of thousands of years and distances reaching hundreds of astronomical units, have their closest approach points clustered in a specific region of space, rather than distributed randomly around the sky, as chance would predict. The probability of this clustering occurring by chance, Brown and Batygin calculated in their 2016 paper, was about 0.007%, roughly 1 in 15,000. A more careful 2019 reanalysis by the same authors, which explicitly modeled the observational biases in how distant Kuiper belt objects had been discovered, brought the figure down somewhat to about 1 in 500, still small enough to make an uncomfortable explanation. The response from the planetary science community was immediate and divided. Some researchers found the statistical argument compelling and the Planet 9 hypothesis a natural explanation. Others questioned the statistical analysis, pointing out that the objects used in the calculation were not discovered in an unbiased survey, that observational selection effects could have artificially created the apparent clustering, and that when selection effects were properly accounted for, the statistical significance of the clustering was much reduced. Renu Malhotra, a planetary scientist at the University of Arizona, who had done foundational work on Kuiper belt resonances in the 1990s, offered an alternative in 2016. Rather than a single large distant planet, the clustering might reflect the combined gravitational influence of several smaller undiscovered bodies in the trans-Neptunian region. Scott Shepard at the Carnegie Institution for Science has continued to discover new extreme trans-Neptunian objects that refine and complicate the clustering picture, with some new objects consistent with Planet 9's predicted influence, and others less so. The hypothesis remains unconfirmed. The proposed planet has not been directly detected. No telescope has imaged it. No spacecraft has detected its gravitational influence on its own trajectory, though New Horizons scientists have used the spacecraft's precisely known trajectory to place constraints on the possible mass and location of any undiscovered planet along its path. The constraints are not yet tight enough to rule out Planet 9's existence, but continued tracking of New Horizons' trajectory over the coming years will improve the limits. What makes the Planet 9 hypothesis so persistent, despite the absence of direct detection, is that it is genuinely predictive. It makes specific, testable predictions about where additional extreme trans-Neptunian objects should be found, in which parts of the sky, at which distances, with which orbital characteristics. As surveys like the Vera C. Rubin Observatory expand the census of the outer solar system, those predictions will be tested. If the predicted objects appear in the predicted locations, the hypothesis will gain substantial credibility. If they do not, it will fade. The Kuiper cliff, the sharp drop in object density at 50 astronomical units, is one of the phenomena that Planet 9, in some versions of the hypothesis, could help explain. If the proposed planet's gravitational influence has been sculpting the outer Kuiper belt over billions of years, it might have swept objects out of certain orbital regions, creating the apparent edge at 50 astronomical units. Alternatively, it might have trapped objects in specific resonances, creating the cluster of distant bodies at 70 to 90 astronomical units that the Subaru Hypersuprime Cam survey is beginning to detect. But the Planet 9 hypothesis is not the only proposed explanation for the cliff and the distant clustering. Neptune alone may be sufficient. Its resonances and its gravitational stirring over billions of years may have created the observed distribution without requiring any additional undiscovered body. And the recent Subaru discoveries of objects at 70 to 90 astronomical units, coming as they do from a telescope operating near the limits of current sensitivity, may simply represent the bright end of a continuous distribution that extends the belt smoothly from its inner edge to much larger distances. The situation, honestly assessed, is one of multiple competing hypotheses, each consistent with some of the available evidence and inconsistent with other parts of it, awaiting the larger dataset that will allow discrimination. This is not a failing of science. This is science operating exactly as it should, generating hypotheses, accumulating evidence, and patiently waiting for the observations that will reduce the number of viable explanations from several to one. Here is where we encounter something that rewrites the significance of everything discussed so far. The cold, classical Kuiper belt objects, the most pristine, least disturbed, most ancient material in the solar system, are not randomly distributed in color. They are systematically, strikingly red. That deep, Tholin's rich red that Arakoth displays is not unique to Arakoth. It is characteristic of the cold classical population as a whole. The cold classicals are the reddest objects in the solar system, not just a little redder than other outer solar system objects. Dramatically, unusually, statistically significantly redder. The hot classical objects, by contrast, have a broader range of colors. Some red, some more neutral, some bluish. The scattered disk objects show a similar spread. Pluto itself, despite being associated with the Kuiper belt, has a complex color pattern driven by its volatile cycle. But the cold classicals are consistently, almost uniformly red, with a color distribution that clusters tightly around the properties of fresh tholins. This color uniformity is itself a discovery. It is not what you would predict if the cold classicals were a random sample of the original protoplanetary disk material. You would expect a distribution of colors reflecting a distribution of formation distances, a gradient of initial compositions. Instead, the cold classicals appear chemically homogeneous, drawn from a relatively narrow range of formation conditions, as if they all originated in approximately the same part of the disk. And here is the deeper implication. The streaming instability, the gravitational collapse mechanism that Arakoth confirmed, tends to form binaries from material in a compact local cloud. If the cold classicals all formed in a similar part of the disk and were then preserved in their current low-inclination orbits without significant dynamical disturbance, then their color homogeneity is exactly what you would predict from the streaming instability model operating in a specific zone of the protoplanetary disk. But the streaming instability requires certain conditions to operate. It requires a locally elevated density of solid particles relative to gas. a concentration that can arise spontaneously through the dynamics of particle drift in a protoplanetary disk, but only under conditions that depend on the local pressure gradient, the particle size distribution, and the ratio of solid to gas in the disk. If the cold classicals were formed by streaming instability in a specific zone, that zone had to have the right conditions. And those conditions were not universal. They were specific to a particular region of a particular disk at a particular time. This means that the cold classical Kuiper belt is not just an archive of the solar system's early material. It is a record of the specific conditions under which planetesimal formation through streaming instability was triggered. It is, in a sense, a laboratory notebook left over from the experiment that built the solar system, recording not just the materials used, but the conditions under which the reaction ran. Reading that notebook fully will require knowing the compositions of many more cold classical objects in detail, more JWST spectroscopy, more survey discoveries, more compositional mapping. But the framework for interpreting the data is now clear, and the data is beginning to flow. Something here deserves attention. Something that has been implicit throughout everything discussed, but that becomes explicit only when you step back and look at the whole arc of Kuiper belt discoveries over the last 30 years. The Kuiper belt was predicted to exist before it was observed. The prediction was based on theoretical reasoning about where the building blocks of planets would have been frozen in place by the conditions of the early solar system. The prediction was confirmed, slowly, by surveys that accumulated objects one by one. Those objects were studied and classified, and the classification revealed a dynamical structure that reflected the history of the giant planet's migration. That migration history was reconstructed from the belt structure, and the reconstruction revealed a solar system far more dynamic and chaotic in its youth than anyone had suspected. The objects in the belt were then studied up close, first by New Horizons, now by JWST, and their physical properties confirmed and extended the dynamical story, adding chemical and geological detail that the orbital data alone could not provide. At every step, the new observation was consistent with and enriched by the previous observations. The whole picture is coherent. The pieces fit together, and the picture they form is of a solar system whose current orderly appearance is the product of a violent, chaotic youth, a period of giant planet migration, of massive gravitational stirring, of objects scattered and ejected and redistributed, and whose outer frontier still carries, frozen in ice and organic chemistry, the memory of that violent beginning. That is the story the Kuiper belt is telling, not just the story of individual objects, but the story of the solar system's entire formative history. And it is a story that is still being read. New Horizons found 2 pairs of Kuiper belt object binaries, small bodies that orbit each other so closely that these tight twins cannot be seen as separate objects from any observatory on Earth or in Earth orbit. Arakoth may be a highly porous object with a bulk density similar to that of settled snow. That last detail, the density of settled snow, is one of those numbers that shifts the intuitive picture of what a Kuiper belt object actually is. When you imagine a rocky body in space, you probably imagine something hard and dense, a chunk of stone or metal. Arakoth is neither. It is extraordinarily porous, a loosely bound aggregate of ice and dust, held together primarily by its own feeble gravity and by the gentle cohesive forces between its constituent particles. If you could somehow pick it up, it would feel more like a dry sponge than a rock. It would crumble under pressure that would leave granite untouched. This porosity is not surprising, given the formation mechanism. If Arakoth formed through the gravitational collapse of a cloud of particles without energetic collisions, then its interior was never compacted by impact. It retains the loose, porous structure of the original aggregate, the structure of dust grains gently settling against one another under their own self-gravity, with voids between them larger than the grains themselves. The bulk density of settled snow, roughly 150 to 300 kilograms per cubic meter, compared to rock at roughly 3,000, means that Arakoth is mostly empty space. Most of its volume is occupied not by solid material, but by void. This has implications for how it responds to the various environmental stresses acting on it. The thermal cycling of rotation, the faint tidal forces of the distant sun, the micro-impacts of interplanetary dust. A porous, snow-like body responds to these stresses differently than a solid rock would, and the response shapes the slow evolution of its shape and surface structure over billions of years. It also has implications for understanding what happens when comets, which are themselves Kuiper belt, objects that have been diverted into the inner solar system by gravitational interactions, interact with the Sun. If cold classical Kuiper belt objects like Arakoth are representative of the primordial material from which comets are built, then the porosity and low density of Arakoth are properties shared by the nuclei of comets. And indeed, the measurements made by the European Space Agency's Rosetta mission at Comet 67P/Churyumov-Gerasimenko, a Jupiter family comet that originated in the Kuiper belt, revealed a nucleus with a bulk density of roughly 500 kilograms per cubic meter, about twice that of settled snow, but still far below anything you would call rock-like. Fluffy, porous, loosely bound, consistent with formation through gentle accumulation of particles rather than violent collision. The connection between Kuiper belt objects and comets is not merely structural, it is chemical. The molecules detected in the coma of comets, the cloud of gas and dust that surrounds the nucleus when a comet approaches the Sun and its ices begin to sublimate, include water, carbon dioxide, carbon monoxide, methane, methanol, formaldehyde, hydrogen cyanide, glycine, and dozens of other organic molecules. Many of these are the same molecules detected on the surfaces of Kuiper belt objects by JWST. The coma of a comet is, in a sense, the chemical inventory of the Kuiper belt revealed in real time, as solar heating liberates the molecules that have been locked in ice for billions of years. This matters for the question of life's origins on Earth. The delivery of organic molecules and water to the early Earth by comets, objects from the Kuiper belt, is one of the standard mechanisms invoked to explain how the building blocks of biology arrived on a planet that formed in the hot, dry inner solar system. If Kuiper belt objects are rich in the molecular precursors to biology, and if comets transport those precursors inward to the terrestrial planets, then the Kuiper belt is not merely the archive of the solar system's early history. It is part of the causal chain that produced life on Earth. The chain runs from the streaming instability that formed the cold classical objects to the dynamical processes that diverted some of them into cometary orbits to the delivery of their organic cargo to the early Earth. 4.5 billion years of chemistry, preserved in ice, ultimately contributed to the emergence of organisms capable of sending spacecraft back to examine the ice from which they came. Now we reach what may be the most intellectually vertiginous implication of the Kuiper belt's extended structure: the possibility that the solar system's outer architecture has been misread, not just in scale, but in kind. The classical picture of the outer solar system has three distinct zones: the Kuiper belt, ending at roughly 50 astronomical units, the scattered disk, with objects on highly eccentric orbits reaching to hundreds of astronomical units, and the Oort cloud, a vast spherical shell of comets at thousands to hundreds of thousands of astronomical units, the source of long-period comets. But the discovery of objects like Sedna, with a perihelion of 76 astronomical units, far too distant to have been scattered there by any known planet's gravitational influence in its current orbit, and the proposed second Kuiper belt population at 70 to 90 astronomical units has begun to suggest that the boundaries between these three zones are not as clearly defined as the classical picture assumed. There may be a fourth zone, a population of objects at intermediate distances, beyond the classical Kuiper belt, but well inside the Oort cloud, that reflects a period of the solar system's history not captured in the three-zone model. Some researchers call this population the inner Oort cloud, or the Hills cloud, proposed theoretically by Jack Hills in 1981. Others call it the detached population, referring to the fact that these objects have perihelia detached from Neptune's gravitational influence, too far from Neptune to have been scattered there by that planet in its current orbit, but not far enough to belong to the Oort cloud's enormous spherical shell. The origin of these detached objects is genuinely mysterious. One possibility, consistent with the Planet 9 hypothesis, is that an undiscovered large planet sculpted their orbits. Another possibility, proposed by researchers including Hal Leveson at the Southwest Research Institute and Alessandro Morbidelli at the Observatoire de la Côte d'Azur in Nice, France, is that the Sun formed in a star cluster, a densely packed environment of young stars, and that the gravitational influence of neighboring stars during the Sun's infancy lifted the perihelia of some scattered disk objects to large distances, creating the detached population. The Sun has long since dispersed from its birth cluster, but the objects whose orbits were modified during that early dense environment remain, carrying in their orbital elements the memory of a time when other stars passed close enough to the solar system to leave gravitational fingerprints. This is perhaps the deepest finding buried in the Kuiper belt data. The possibility that the outer solar system remembers the Sun's birth cluster, that the orbits of distant objects like Sedna encode information about the stellar environment in which the Sun spent its first 100 million years. By reading those orbits carefully, by finding more Sedna-like objects, by characterizing their distribution in the sky and their orbital parameters in detail, it may be possible to reconstruct something about the density and structure of the cluster in which our Sun was born. No other approach currently available to astronomy can provide this information. The birth cluster itself is gone, its member stars dispersed across thousands of light years of the Milky Way over 4 billion years of galactic dynamics. The stars that once neighbored the Sun cannot be identified with certainty, but their gravitational influence may persist, encoded in the orbits of frozen worlds, drifting in the cold dark of the outer solar system. The Kuiper belt and its associated populations are, in this interpretation, not just an archive of solar system history. They are an archive of stellar neighborhood history, a record of the social environment in which our Sun spent its youth, preserved in the orbital elements of objects that have been drifting, undisturbed, ever since. What happens next? What does the current generation of instruments bring? What does the future of exploration and observation bring? What does the patient accumulation of data and models and understanding bring when turned toward the outer solar system? What happens when the Vera C. Rubin Observatory begins its full survey operations, and the number of known Kuiper belt objects jumps from the current few thousand to tens or hundreds of thousands? What happens to the statistical picture of the belt structure, the clustering of distant objects, the population of the gap region, when the sample size increases by 2 orders of magnitude? What happens when JWST completes its first systematic survey of Kuiper belt object compositions and the chemical map of the belt comes into focus? When the correlation between composition and orbital family becomes clear enough to trace the dynamical history of individual objects from their birth locations in the protoplanetary disk to their current positions. What happens if New Horizons detects, as it moves outward, a clean boundary to the Kuiper belt dust, a distance at which the elevated dust flux finally drops to the interstellar background, marking the true outer edge of the Kuiper belt population? Or what happens if it does not? If the elevated dust flux continues all the way to the heliopause, suggesting that the outer solar system is populated with objects all the way to the boundary of the Sun's influence? What happens if a future survey finally detects Planet 9? A faint, slow-moving point of light in a specific patch of sky, consistent with the orbital predictions, and the missing massive body resolves from a hypothesis into a world. What happens to the Kuiper belt model, to the understanding of the scattered disk, to the interpretation of Sedna and the other detached objects, if a 10th planet is confirmed? Or what happens if no such planet is found? If the Vera C. Rubin Observatory surveys the entire sky to the required depth and finds nothing consistent with Planet 9, and the clustering of distant objects must be explained some other way, and the solar system proves to have only 8 full-sized planets after all? What does it mean if the outer Kuiper belt's chemical composition reveals, through JWST spectroscopy, a distinct boundary between two populations, an inner population formed in one part of the protoplanetary disk, and an outer population formed farther out, separated by a gap that reflects a specific event in the disk's history? Perhaps a gap cleared by a forming planet that later migrated inward. And here is the question that none of these instruments can answer, and that no foreseeable technology can answer, and that we must simply hold in the mind as a genuine epistemological limit. What lies between the outer Kuiper belt and the inner Oort cloud? The region from roughly 100 to roughly 2,000 astronomical units is almost entirely unconstrained by current observations. Objects in this region move too slowly to be detected by their motion against the background stars in a single survey campaign, and they are too faint for current instruments to detect directly. This region, larger in volume than the entire volume of the known solar system, is essentially invisible to us. We cannot know what is there. We cannot know whether it is empty, populated with a thin scattered disk, rich with a previously unknown belt, or home to the hypothetical Planet 9 itself. We cannot know. That phrase, repeated with emphasis, is not a counsel of despair. It is a description of genuine scientific frontier, the edge beyond which current knowledge does not extend, and beyond which future knowledge will eventually reach. Every generation of astronomers has faced such a frontier. Every generation has pushed it outward. The frontier facing this generation is the outer solar system's hidden architecture and the tools being deployed. JWST, the Vera C. Rubin Observatory, New Horizons' continued journey, are the most powerful ever brought to bear on it. What comes back will surprise us. It always does. Picture yourself standing on a hillside at night, somewhere far from the nearest city, where the sky is genuinely dark and genuinely full. You have been lying on your back for an hour, watching the stars wheel slowly overhead, and your eyes have adjusted to the darkness, to the point where the Milky Way is not just a smear, but a structure. A thick, luminous river of light, with texture and depth, with dark lanes of dust cutting through it, with concentrations and voids that your dark adapted eyes can resolve into something close to three-dimensional. Now find the place in the sky where Pluto is tonight. You cannot see it, of course. It requires a large telescope and precise coordinates and a sensitive camera to detect Pluto's faint reflected light. But you can find the approximate region, a patch of sky like any other patch, indistinguishable from the darkness around it. And beyond that point, another 4 billion miles farther, the Kuiper belt is drifting in its slow, ancient procession. Hundreds of thousands of frozen worlds, ancient red snowmen, porous aggregates of ice and organic chemistry. Binary pairs drift in quiet mutual orbit, red lobe circling red lobe, undisturbed since they first touched 4.5 billion years ago. And still farther out, in the gap where the models said there should be almost nothing, something. A cluster of objects at 70 to 90 astronomical units, detected only recently, still incompletely characterized, pointing toward a structure in the outer solar system that the standard picture does not accommodate. And still farther, the boundary where the sun's influence gives way to the galaxies, where the solar wind dies against the pressure of the interstellar medium, and the true nature of our solar system's outer wall comes into focus. Stay with this picture for a moment. Not the numbers, not the astronomical units and the kilometers per second, and the collision rates and the spectral indices, but the physical reality they describe. A vast, cold, dark, ancient, crowded place. Quiet in a way that no environment on Earth is quiet. Old in a way that no artifact of human civilization is old. Full of information encoded in the shapes of ice and the colors of organic chemistry, waiting for the instruments sensitive enough to read it. This is what NASA found beyond Pluto. Not just specific objects with specific properties, but an entire dimension of the solar system that was invisible to us a generation ago and is only now being revealed, layer by layer, measurement by measurement, in the data streaming back from a spacecraft the size of a grand piano and the observations accumulating in the archives of the world's most powerful telescopes. There is a concept in the history of science that philosophers call a gestalt shift, the moment when a collection of disparate, confusing, seemingly unrelated observations suddenly reorganizes itself into a coherent picture. The moment when the noise becomes a signal. When the puzzle pieces, assembled patiently over years of work by dozens of researchers, suddenly reveal the image they were always forming. The Kuiper belt has been undergoing such a reorganization for the last 10 years, and it is not yet complete. But the outline of the new picture is clear enough to trace. The old picture was this. The solar system has a modest, relatively thin belt of icy debris beyond Neptune, extending to about 50 astronomical units, which is the remnant of the outer protoplanetary disk. The objects there formed slowly through collisional accretion, were stirred by Neptune's migration, and have been gradually grinding themselves down through further collisions ever since. The belt ends at 50 astronomical units because the protoplanetary disk simply ran out of material there. And beyond that boundary, the solar system is essentially empty until the Oort cloud at thousands of astronomical units. The new picture is this. The solar system has an outer architecture that extends substantially farther than 50 astronomical units, perhaps to 80, perhaps to 90, perhaps to distances we have not yet characterized. The objects in the innermost part of this extended structure formed not through slow collisional accretion, but through rapid gravitational collapse, gently and efficiently, in a way that preserved their primordial composition almost perfectly. Their chemical properties encode the compositional gradient of the original protoplanetary disk and the dynamical history of the giant planet migration that reshaped the outer solar system in its first billion years. The apparent cliff at 50 astronomical units is not the edge of the solar system's material. It is a gap, a valley in the distribution of objects, beyond which a second population exists. The total mass of the outer solar system's small body population may be substantially larger than the truncated picture implied, and our solar system may be more comparable in its outer architecture to the debris disk systems observed around other stars than the old picture suggested. And threaded through all of this, the most recently discovered, the most incompletely understood, the most far-reaching in its implications, is the possibility that the outermost objects, the Sedna-class bodies with their extreme detached orbits, carry in their orbital elements the memory of the Sun's birth cluster. The memory of a time 4.5 billion years ago when other stars were close enough to leave gravitational fingerprints on the outermost reaches of the solar system. That last possibility is the most philosophically striking thing in this entire story, because if it is true, if the orbits of distant icy worlds in our own backyard preserve information about the stellar neighborhood of the Sun's infancy, then the Kuiper belt is not just an archive of the solar system's history. It is a message from the wider galaxy, a record of the Sun's origins, encoded not in the chemistry of stars or the spectra of ancient light, but in the patient, quiet trajectories of frozen objects drifting in the dark. Now we turn to the people who did this work, not the spacecraft and the telescopes, the instruments, but the humans behind them. Because the history of Kuiper belt science is, like all science, a human history. It is the history of individual careers built around specific questions, of theoretical predictions made decades before they could be tested, of observational campaigns conducted at the limits of available technology, of arguments between competing interpretations that sometimes lasted years before the data provided resolution. Kenneth Edgeworth was a retired Irish Army officer turned amateur astronomer who in 1943 proposed, in a paper published in the Journal of the British Astronomical Association, that the region beyond Neptune ought to be populated with a belt of small icy bodies, the source of short-period comets. His argument was based on theoretical reasoning about the distribution of mass in the outer solar nebula, and it was essentially correct. But Edgeworth was working outside the mainstream of professional astronomy, in a period when the outer solar system was considered a solved problem, and his proposal received little attention at the time. Gerard Kuiper, working at the Yerkes Observatory in Wisconsin in 1951, made a similar proposal that a belt of icy bodies beyond Neptune was the source of short-period comets, and his paper appeared in a more prominent venue and in a period when the question was more actively discussed. The belt was subsequently named after Kuiper, though Edgeworth's prior contribution has led many astronomers to prefer the name Edgeworth-Kuiper belt, and the term trans-Neptunian object is recommended by several scientific groups as a less controversy-laden alternative. David Jewett and Jane Liu, working in Hawaii in 1992, made the first confirmed observational detection of a Kuiper belt object beyond Pluto, the object now called Albion, after a systematic survey using the University of Hawaii's 2.2-meter telescope on Mauna Kea. Jewett had been searching for trans-Neptunian objects since 1987, using the best available technology before the first detection came. 5 years of careful, systematic survey work, looking for objects that the theory said should be there, but that the instruments could barely see. The persistence required for that kind of work, the willingness to spend years searching for something that may or may not exist, is one of the qualities that distinguishes great observational scientists. Renu Malhotra at the University of Arizona in 1993 and 1995 developed the theoretical framework explaining how Neptune's outward migration produced the resonant structure of the Kuiper belt, why Pluto and the Plutinos are trapped in the 2 to 3 resonance with Neptune, and what this tells us about the history of Neptune's orbital evolution. Her work transformed the Kuiper belt from a static fossil to a dynamic record of planetary migration, and it laid the conceptual foundation for everything that followed in understanding the belt's structure. Alan Stern, the principal investigator of New Horizons, spent the 1990s and 2000s advocating for a dedicated mission to Pluto and the Kuiper belt against significant institutional resistance. The first New Horizons proposal was rejected. The second was also rejected. The mission was eventually approved in 2001 after years of advocacy, and the spacecraft launched in 2006. The patience and determination required to see a mission from initial proposal to launch, to maintain scientific vision and institutional momentum across a 15-year period of uncertainty, represents a kind of intellectual commitment that rarely receives the recognition it deserves. And Will Grundy of the Lowell Observatory in Flagstaff, Arizona, the same observatory where Clyde Tombaugh discovered Pluto in 1930, has spent his career studying the compositions of Kuiper belt objects through spectroscopy, building the observational foundation that JWST is now extending with unprecedented sensitivity. His work on Kuiper belt binary orientations provided evidence for the streaming instability formation mechanism that Arakoth later confirmed so dramatically. These are the people who built the picture, not all at once, not in a single moment of genius, but through decades of patient, careful, rigorous work at the limits of available technology. Their individual contributions are the individual tiles of a mosaic, and the mosaic they form is one of the most remarkable achievements in the history of planetary science. Consider, briefly, a parallel from the history of exploration, not scientific exploration, but the physical exploration of unknown territory, that captures something of what the Kuiper belt story represents. In 1820, the interior of Antarctica was entirely unknown. The continent itself had barely been confirmed to exist, with competing claims about who first sighted land through the Antarctic ice. The maps of the time showed a white void in the southern polar regions, not a blank labeled unknown, but literally white space, the absence of information rendered as the absence of territory. Some cartographers placed a hypothetical southern continent there, based on theoretical arguments about the need for a landmass to balance the northern polar region. Others left the space genuinely empty. Over the following century, expeditions from Britain, Norway, the United States, and other nations gradually revealed what lay beneath the ice. The coast was mapped. The interior was traversed. The first men reached the South Pole in 1911, Roald Amundsen arriving 34 days before Robert Falcon Scott's doomed party. The continent's physical properties were characterized: its ice sheet, its mountain ranges, its subglacial lakes, its atmospheric circulation. And what was found was not what anyone had predicted. Not the temperate, fertile land that some theorists had imagined, but a brutally cold, wind-scoured, ice-buried continent of extraordinary scientific value, preserving in its ancient ice cores a record of Earth's climate going back 800,000 years. The parallel to the Kuiper belt is imperfect, as all parallels are, but it captures something true. The white space on the map was not empty. The theoretical predictions were partially right and partially wrong in ways that nobody anticipated. The actual territory turned out to be older, colder, more preserved, and more scientifically valuable than any of the pre-exploration theories suggested. And the exploration itself, the physical engagement with the territory, was the only way to know. There is no substitute for going there. There is no substitute for the in situ measurement, the close flyby, the direct observation of surface features that were invisible from Earth. The Kuiper belt, like Antarctica, could be theorized about from a distance for decades without revealing what it actually is. It took New Horizons, an instrument that went there, that moved through the region, that flew 3,500 kilometers from Arakoth's surface, to reveal what the theory could only approximate. And just as the exploration of Antarctica did not end with Amundsen and Scott reaching the pole, the exploration of the Kuiper belt does not end with New Horizons and Arakoth. It is a beginning. The first close look at the first cold classical Kuiper belt object ever visited. One object among hundreds of thousands. A single page of a book that is 4.5 billion years long. Carry everything forward now. The formation story, the dust measurements, the distant objects, the extended belt, the chemical diversity revealed by JWST, the connection to comets and to the origins of Earth's water and organic chemistry, the possible memory of the Sun's birth cluster in the orbits of distant frozen worlds. Carry all of it and ask the question that all of it is building toward. What does it mean? Not in the narrow technical sense. Not, what does the dust count at 55 astronomical units mean for the mass estimate of the extended Kuiper belt? But in the wider, deeper sense. What does it mean for our understanding of what the solar system is, where it came from, and what its existence implies about the broader universe of planetary systems? Here is what the Kuiper belt reveals, stated as directly as the evidence permits. The solar system's current orderly appearance, the neat arrangement of planets in nearly circular orbits in a thin plane, the relatively quiet asteroid belt, the thin disk of Kuiper belt objects, is not the solar system's natural state. It is the outcome of a violent, chaotic process that transformed a dynamic, unstable young system into the stable, middle-aged system we inhabit today. The evidence for that transformation is written in the orbital structure of the Kuiper belt, in the resonant populations trapped by Neptune's migration, in the scattered disk objects flung to extreme distances by gravitational encounters, and in the cold classicals preserved in their pristine orbits as witnesses to the state of things before the storm. The materials that built the solar system, the ices and organics frozen into planetesimals in the outer disk, were not destroyed by the planetary formation process. They were redistributed. Some became the cores of the giant planets. Some were scattered to the Oort cloud. Some were diverted inward as comets and contributed their cargo of water and organic molecules to the inner planets, including Earth. And some were preserved, essentially untouched, in the quiet orbits of the cold classical Kuiper belt, waiting for the instruments that could read them. Those instruments have now arrived. They are reading. And what they are reading is not just the history of the solar system, but a story that belongs to a larger narrative. The story of planetary formation operating throughout the galaxy, producing systems whose outer architectures carry the signatures of their histories in the properties of their small bodies. We live in a solar system whose past is preserved in its present. The ancient violence of the giant, planet migration, the gentle primordial formation of Arakoth, the cosmic radiation chemistry of 4.5 billion years, all of it is there in the outer solar system, patient and cold and still. And a spacecraft launched by human hands is moving through it right now, listening, measuring, transmitting. The universe keeps records. We are learning to read them. There is a particular quality to the darkness of the outer solar system that deserves a moment of direct attention. Not a technical discussion, not an analysis of photon flux or solar constant values, but a simple acknowledgement of what it is like out there, physically, in the reality that the numbers describe. At the distance of the Kuiper belt, say 45 astronomical units from the Sun, where New Horizons spent several years gathering data, the Sun delivers about 1/900th of the light and heat it delivers to Earth. That ratio is difficult to translate into a sensory experience, but here is an approach. On a bright, clear day on Earth, you can feel the warmth of sunlight on your skin within seconds of stepping outside. You can read a newspaper from any angle. You can squint into it and see a blazing disk that fills your vision with white fire. At 45 astronomical units, that same sun is a star. A very bright star, the brightest in the sky by far, and still capable of illuminating the surfaces of nearby objects to the level of a moonlit night on Earth. But a star, a point of light, not a disk. No warmth perceptible to human skin. The temperature of the surrounding vacuum has dropped to roughly -220 degrees Celsius. Any exposed surface equilibrates to that temperature, unless heated from within by residual radioactivity or tidal flexing. In this near-absolute cold, the ices on the surfaces of Kuiper belt objects are essentially permanent. Water ice at -220 degrees does not sublimate on any timescale relevant to the age of the solar system. Methane ice, nitrogen ice, carbon monoxide ice, these are more volatile, and they do sublimate slowly even at Kuiper belt distances, which is why only the largest Kuiper belt objects retain them on their surfaces. But water ice and the complex organic tholins built up from centuries of radiation processing are stable. They will persist essentially unchanged for as long as the solar system endures. This stability is what makes the Kuiper belt scientifically irreplaceable. The record it preserves is not degrading. It is not being erased by geological activity or weathered by atmosphere or altered by the heat of a nearby star. It is sitting there in the cold, intact, exactly as it was assembled 4.5 billion years ago, waiting. And the waiting is almost over. Not in a human lifetime sense, not in a generation, not even in several generations, will we exhaust the scientific possibilities of the outer solar system. But in the sense that matters scientifically, the instruments now exist that can read what was previously unreadable. The spacecraft that can go there exists, and it is already there. The telescopes with the sensitivity to characterize the chemistry of distant icy worlds exist, and they are operating. The survey telescopes that will expand the census of known objects by 2 orders of magnitude are coming online. The waiting, the long wait of 4.5 billion years for something with eyes and curiosity to arrive, is meeting its end in the data being gathered right now, in the papers being written right now, in the careers of young researchers being launched right now, who will spend the next 40 years reading the record that the outer solar system has been keeping since before the Earth had an ocean. This is, by any measure, one of the most remarkable moments in the history of planetary science. And it is happening quietly, in the cold, in the dark, 5 billion miles away from where you are lying right now. The solar system does not end at Pluto. It never did. That was always the map's limitation, not the territories. What lies beyond Pluto is not a margin, not a void, not the end of something. It is an archive, the most ancient, most complete, most chemically intact archive in the known solar system, assembled in the first moments of the Sun's existence and preserved with extraordinary fidelity through 4.5 billion years of cold and dark. It is a place where the building blocks of worlds are still present in the form they first took, when gravity and chemistry conspired to assemble them from the raw material of a collapsing nebula. It is a place where the violence of the solar system's youth left permanent signatures in the orbital elements of scattered objects and resonant populations. And it is a place where the Sun's own birth, its emergence from a dense stellar cluster 4.5 billion years ago, among stars whose identities have long since been lost to galactic dynamics, may be encoded in the extreme orbits of detached frozen worlds, drifting in silence at distances that make the mind reach and find no familiar foothold. Everything we have traced through this exploration comes to rest here, in a few essential truths that emerge from the accumulation of discoveries. The first truth is about formation. Arakoth, that ancient, red, porous, snowman-shaped object visited by New Horizons on New Year's Day 2019, settled a decades-long argument about how the building blocks of planets are made. Not through violent collisions, but through gentle gravitational collapse. Not through a chaotic demolition derby of impacts, but through the quiet settling of particles in a local cloud, forming binary pairs that drifted together over millions of years, and finally, unhurriedly, touched. The shape of Arakoth supports a theory of Kuiper belt object formation, where objects in the early solar system formed rapidly from the collapse of a local region of dust, and often formed two binary objects revolving around one another. That finding reaches backward through 4.5 billion years to the moment of the solar system's assembly, and forward to every planetary system forming around every star in the galaxy. The mechanism is not unique to us. It is the mechanism. And we know it because one small spacecraft flew close enough to see the shape of one ancient snowman in enough detail to read the story written in its geometry. The second truth is about preservation. The Kuiper belt's cold classical objects, red, binary-rich, dynamically quiet, orbiting in the same gentle paths they have occupied since the protoplanetary disk era, are not merely old. They are functionally unchanged. One of the class of bodies called cold classical Kuiper belt objects, Arakoth is an ancient relic preserved from the time when the planets first began to form nearly 4.5 billion years ago. The red color of their surfaces, that deep, Tholin's-rich hue produced by 4.5 billion years of cosmic radiation chemistry, is the color of time itself, made visible. New Horizons found that the surface of Kuiper belt object Arakoth is uniformly coated by red-colored methanol ice. Those molecules, that chemistry, that color, they are the solar system's earliest surviving handwriting, and JWST is now learning to read it letter by letter, molecule by molecule, in the infrared spectra of dozens of objects whose surfaces have never been touched by warmth. The third truth is about scale. Speeding through the outer edges of the Kuiper belt, almost 60 times farther from the Sun than Earth, the New Horizons Venetia Burney Student Dust Counter instrument is detecting higher than expected levels of dust, and the readings defy scientific models that the Kuiper belt object population and density of dust should start to decline 1 billion miles inside that distance, contributing to a growing body of evidence that suggests the outer edge of the main Kuiper belt could extend billions of miles farther than current estimates, or that there could even be a second belt beyond the one we already know. The solar system is larger than the diagram. It was always larger than the diagram. The white margin at the edge of the poster was not empty space. It was the limit of our instruments, mistaken for the limit of the territory. As Wes Fraser of the National Research Council of Canada noted, our solar system's Kuiper belt long appeared to be very small in comparison with many other planetary systems, but the results suggest that idea might just have arisen due to an observational bias. The true outer architecture of our solar system, its full extent, its second population, its detached objects with their extreme orbits, its connection to the birth cluster where the Sun spent its infancy. is still being revealed. The map is still being drawn. The fourth truth is about connection. The organic molecules frozen into Kuiper belt objects, the tholins, the methanol, the carbon dioxide and carbon monoxide ices, the complex aliphatic organics detected by JWST, are not merely chemical curiosities. They are part of a delivery chain that reaches from the outer solar system to the surfaces of the inner planets, including Earth. Comets, diverted from the Kuiper belt by gravitational interactions, have been transporting these molecules inward for billions of years, contributing to the chemical inventory of the early Earth and possibly contributing to the conditions under which life arose. The distant world has likely changed very little since its formation near the solar system's birth, so it functions as a time capsule of sorts from that ancient milieu, and the view of that ancient world points clearly to a past where objects like it formed from the direct collapse of the original solar nebula. The Kuiper belt is not separate from the story of life on Earth. It is part of that story. The carbon in every organic molecule, in every living cell on this planet, passed through the outer solar system on its way here, locked in ice, carried by a comet, delivered to the young Earth by an impact that nobody witnessed, and that left no record except the chemistry of everything that came after. The fifth truth is about humility. Based on estimations of the primordial mass required to form Uranus and Neptune, as well as bodies as large as Pluto, earlier models of the Kuiper belt had suggested that the number of large objects would increase by a factor of 2 beyond 50 astronomical units, so this sudden drastic fall-off, known as the Kuiper cliff, was unexpected, and to date its cause is unknown. Unknown. After 30 years of study, after the deployment of the most sensitive telescopes and the only spacecraft ever to traverse the region, the cause of the most prominent structural feature of the outer solar system remains unknown. The readings contribute to a growing body of evidence that suggests the outer edge of the main Kuiper belt could extend billions of miles farther than current estimates, or that there could even be a second belt beyond the one we already know. The second belt, if it is real, if it is distinct, if it represents a genuine second population rather than an extended single population, has not yet been confirmed. The Planet 9 hypothesis remains unconfirmed. The origin of the anomalous cosmic optical background detected by New Horizons remains unexplained. New Horizons recently obtained the best ever measurement of the light coming from the distant universe, and the level is double that accounted for by all known galaxies. Double. And we do not know why. This is an honest picture, not a complete picture, not a triumphant picture of a problem solved and a mystery resolved, but an honest one. A picture in which enormous progress has been made, in which the broad outlines of the outer solar system's nature and history are now clear, and in which specific, well-defined questions remain open and are being actively pursued with the best available instruments and the most careful available minds. The spacecraft that did the most to transform this picture is, right now, approximately 5.5 billion miles from Earth and moving outward at roughly 36,000 miles per hour. Currently, in its extended mission, New Horizons is proving to be a resilient spacecraft with hopes of lasting well into the 2040s, and the research team anticipates that, given its current velocity, the spacecraft could reach up to 100 astronomical units from the Sun. Its instruments are still functioning, its dust counter is still counting, its plasma sensors are still sampling the solar wind. Its cameras have been turned toward the distant planets, capturing views of Uranus and Neptune from geometries that no instrument has occupied since Voyager 2 flew by them in 1986. In 2025, The first map of all Lyman alpha emissions in the Milky Way galaxy was published based on New Horizons observations. A spacecraft sent to photograph Pluto, producing the first map of a galaxy's ultraviolet emissions. The serendipity of deep space exploration, the way that instruments sent to answer one question find themselves positioned to answer questions that nobody thought to ask, is one of the most reliable features of the Enterprise. Every mission to the outer solar system has returned discoveries that were not on the original itinerary. Every journey into unknown territory has found things that the map makers did not anticipate. New Horizons will continue moving outward. Its power supply, a radioisotope thermoelectric generator fueled by the decay of plutonium-238, will gradually weaken over the coming decades, reducing the number of instruments that can be operated simultaneously and eventually falling below the threshold required to transmit data. At some point in the 2040s or 2050s, the spacecraft will go silent. It will not stop. It will continue moving outward at 36,000 miles per hour, past 100 astronomical units, past the heliopause, into the true interstellar medium, the space between stars, carrying with it a golden record of human achievement and a small plaque identifying its origin as a message to whatever, if anything, might someday find it in the darkness between the stars. By that time, the Vera C. Rubin Observatory will have been operating for decades, and the number of known Kuiper Belt objects will have grown from thousands to hundreds of thousands. JWST, or its successor, will have completed a systematic compositional survey of the belt and produced a chemical map that traces the thermal and compositional gradient of the original protoplanetary disk across its full radial extent. The Planet 9 hypothesis will have been confirmed or refuted. The second Kuiper belt, if it exists, will have been mapped. The Sun's birth cluster, if its memory is genuinely preserved in the orbits of Sedna-class objects, will have been reconstructed, at least in outline. And somewhere in that accumulated understanding, in the compositional maps and the orbital catalogues, and the dust flux measurements and the spectral analyses, will be a complete account of where the solar system came from, how it assembled itself, how it transformed from a chaotic, violent young system into the orderly, middle-aged system we inhabit, and what that transformation means for the probability of similar outcomes, similar planets, similar conditions, similar opportunities, around the billions of other stars in this galaxy. Look up again at that dark patch of sky, the one above and beyond Pluto's position tonight. You know now that it is not empty. You know that it holds ancient red snowmen drifting in slow orbits, porous and pristine, their surfaces the color of 4.5 billion years of cosmic radiation chemistry. You know that a spacecraft is out there, in that darkness, still moving, still measuring, still finding things that nobody predicted. You know that the apparent edge of the Kuiper belt at 50 astronomical units is not the edge of the solar system's material, but a gap, a valley in the distribution of objects, beyond which something is present, something that the standard picture did not account for. You know that the building blocks of the planets were assembled gently through the quiet gravitational collapse of local particle clouds, not through the violent collisions that earlier models described. You know that the molecules preserved in Kuiper belt ice, the carbon and the oxygen and the complex organic chains, are part of the causal history of life on Earth. You know that the most extreme outer solar system objects, the Sedna-class bodies with their enormous detached orbits, may carry in their trajectories the memory of the stellar neighborhood where the Sun was born. And you know that much of this was unknown a generation ago. 30 years ago, the first Kuiper belt object beyond Pluto had not yet been detected. 20 years ago, no spacecraft had visited the Kuiper belt. 10 years ago, no spacecraft had approached a cold classical Kuiper belt object, and the debate about how such objects formed was unresolved. The pace of discovery in the outer solar system over the last 3 decades is one of the fastest in the history of planetary science. And the pace is accelerating. The tools are better. The spacecraft is there. The telescopes are more sensitive. The algorithms for finding faint, slow-moving objects in deep survey images are more sophisticated. The researchers entering the field now will spend their careers in a period of revelation unlike anything that preceded it. As New Horizons principal investigator Alan Stern reflected, "I never expected that our encounter with Arakoth would be shoulder to shoulder with the Pluto flyby in terms of its importance. I didn't expect to make an earth-shattering discovery about planet formation in the Kuiper belt. And yet, we have." That quality of surprise, the genuine professional astonishment of a scientist confronting data that overturns expectations, is the surest sign that real exploration is happening. Not the confirmation of what was already known, but the discovery of what was not. The outer solar system is full of things that are not yet known, full of objects not yet detected, compositions not yet characterized, orbits not yet measured, structures not yet resolved. The archive is vast. The reading has barely begun. And every night, from every dark hillside on every continent on this small, warm, improbable planet, the light from beyond Pluto arrives, faint, ancient, carrying in its photons the reflected memory of the oldest surfaces in the solar system, and falls on ground that 4.5 billion years ago was part of the same cloud of dust and ice from which Arakoth itself was made. We are not separate from the Kuiper belt. We are made of the same material, assembled by the same processes, products of the same ancient chemistry. The red surface of Arakoth and the carbon in your body share a common origin, a cloud of gas and dust that collapsed slowly 4.5 billion years ago into a star and its retinue of worlds. The solar system did not end at Pluto. The solar system did not end where any map said it ended. It is larger, older, stranger, and more connected to our own existence than the diagram on the classroom wall ever suggested. If this changed how you think about what lies beyond the last planet, then the time was well spent. Thank you for staying in the dark with something this ancient, this cold, and this full of quiet meaning.